গোলেপ করেছো?
হ্যাঁ হ্যাঁ, করে দিয়েছি।
ওই 6 মিনিট পরেই হবে। না, হয়েছে হয়েছে। স্ক্রিনটা শেয়ার করো। না, স্ক্রিন শেয়ার করবো না, মানে গুগল মিটটা বড় বড় করে রাখো।
আচ্ছা। ওপরে বারটা আসছে, আমি সব বন্ধ করে রাখছি, শুধু গুগল মিট, মেল আর লাইভ স্ট্রিমিংটা অন থাকছে।
হুম হুম হুম। ওকে, আমার আমার স্ট্রিমিংটাও কাজ করছে, কোনো অসুবিধা নেই। আমি আপাতত তাহলে তোমারটাই শেয়ার করছি। আমি ইয়েতে দিয়ে দিচ্ছি, টেলিগ্রামে দিয়ে দিচ্ছি।
ঠিক আছে।
Yeah, no problem, no problem. The inaugural session will be for 30 minutes, and I booked for 10 minutes slot, okay, for you. Okay, that's fine, fine. Thank you. Okay, sure. Bye. Thank you. সঞ্চারী, ঠিক আছে, সব ঠিক আছে, আমি ওই লিঙ্কটা দিয়ে দিয়েছি। হ্যাঁ, তুমি হ্যাঁ, তুমি এই লিঙ্কটা একটু স্টুডেন্টদের গ্রুপদের দিয়ে দাও, সার্কুলেট করে। আর যদি সম্ভব হয় আমি সোশ্যাল মিডিয়াতে দিয়ে দিচ্ছি। সঞ্চারী, মিউট করে দিতে পারো। অনেকে লাল লিখে গুড মর্নিং ম্যাডাম। এটা মিউট করা আছে মনে হয়। গুড মর্নিং।
গুড মর্নিং। বলছি তোমাদের 11:30 ছিল না সময়?
হ্যাঁ হ্যাঁ ম্যাডাম, 11:30।
ওকে ওকে, ঠিক আছে।
ঠিক আছে।
সত্যি
Welcome, Mr. Rajesh.
Can you hear me?
Yes, Rajesh, I'm pretty audible. Good morning.
Good morning, sir.
I see your videos.
Okay, I can present. I can change the layout. So. So, Mr. Rajesh, just one question: who will present from your side, you or Mr. Sharma? Okay. Mr. Sharma is here.
Hello, good morning, Raj.
Good morning.
Raj, good morning. Okay, I am audible to you. Am I audible?
Yeah, Peter.
Yes.
Yeah, you're audible.
Okay, thank you.
Yes. Thank you for joining, sir.
Okay.
Good morning, can you hear me? This is Ajit.
Dr. Pujarini, we can start
Raj.
from 11:30 because Vice Chancellor Madam and other distinguished guests already present here.
Should we
Join.
wait for our respected registrar, sir?
I think Registrar Sir already joined.
Okay.
Sir,
Can you hear me?
Registrar Sir, can you hear me? Yeah, Sridhar Babu, you are pretty audible.
Raj, can you just check with Ajit? Can you hear him as well? Ajit Sharma?
Ajit Sharma.
Before
Mr.
we...
Sharma.
Can you unmute Mr. Sharma? Mr. Sharma?
Yes,
Hello.
Mr. Sharma has joined, but I think he's muted.
I cannot find. There is some issue with video, Mr. Sharma, I think. Can you check your video?
Correct. Dr. Andy. Can you hear me?
Yeah. I can hear you. You're audible. So Register sir is already here, so we can
I
start.
think we are good to start. Yeah.
Yeah. Madam, can we start now?
Yes, of course, sure.
Okay, thank you.
Okay. Thank you, ma'am. So good morning to all, ladies and gentlemen. It's a pleasure to invite you to the International Virtual Symposium on Advances in Chemical Sciences. Now, this is going to be day one of our 3-day webinar series, which has been jointly organized by us, the Department of Chemistry, Diamond Harbour Women's University, in association with the Royal Society of Chemistry. We are very fortunate to have on a speaker list a number of eminent scientists who will be presenting various research topics of importance over this 3-day webinar series. And all of this has been organized with the aim of keeping the chemistry community connected despite the COVID pandemic. So thank you all for turning up in such large numbers. And we are particularly grateful to university authorities, especially our Honorable Vice Chancellor, Professor Anuradha Mukhopadhyay, for actively encouraging and helping us to organize this webinar. I hope you'll enjoy the entire webinar series. And to take you further into the inaugural session, may I invite my dear colleague and co-convener of this webinar series, Dr. Rajkumar Nondi. Dr. Nondi, please.
Thank you, Pujarini. Respected Honorable Vice Chancellor, Madam, Professor Anuradha Mukhopadhyay, the Chief Patron of this organizing committee, respected Sir Muhammad Saidur Rahman, Registrar of Diamond Harbour Women's University, respected Dean, Faculty of Science, Professor Sujit Mondal, and other distinguished speakers and their colleagues, and obviously Mr. Rajiv Parishad and Mr. Ajit Sharma from Royal Society of Chemistry. On behalf of the organizing committee of this webinar, it is my privilege to welcome all of you in the first day of this webinar series. It will, in fact, a very pretty good day for us. Almost 420 participants all over the world registered for our webinar series. And it's globally from different places of the world, Algeria, Nigeria, even USA, UK, etc. So in this webinar, I would like to start a very special quote from one of the Nobel laureate, Ben Feringa, who told in his Nobel laureate ceremony that we may have talked in different language all over the world, but the thing is that when we wrote or write something in the board, like in the chemical structure, there is no different language for the chemistry. So for the chemistry, for the science, for the scientists, don't have any borders. We have the colleagues, friends, competitors, labs, and the student all around the world. So with these thoughts, I would like to welcome and congratulate all the participants of this webinar. And this, I hope it will be nice. And I'm very thankful to our Honorable Vice Chancellor for her constant encourage and suggestion for do this one. So with this, I would like to invite Honorable Vice Chancellor, Diamond Harbour Women's University, Professor Anuradha Mukhopadhyay, share her thoughts. Thank you.
Thank you, Dr. Rajkumar Nondi. A very good morning and a warm welcome to all our distinguished guests of today and this webinar, to all the eminent speakers, to all the faculty members of the Department of Chemistry, Diamond Harbour Women's University, to our registrar, Dr. Saidur Rahman, to our dean, Professor Sujit Mondol, all registered participants, scholars, and students. As you may know, that this university is a very young university, and the Department of Chemistry is younger still. In fact, it's just over a year that permanent faculty members, just a handful of them, have been inducted into our department. And I must congratulate them for being enthusiastic, enterprising, as well as diligent to be able to organize this webinar series, as well as an international seminar in the conventional mode, which was organized by them just a few months back before the lockdown period started due to the pandemic. And I hope that with their diligence and enterprise, our chemistry department will develop and develop fast. This webinar series on International Virtual Symposium on Advances in Chemical Sciences is a 3-day web series, as you have already heard, and it targets a broad audience across all disciplines of chemistry. And the lectures will be delivered by distinguished scientists, which we hope will motivate young students to pursue this line, this discipline of chemistry, and carry on with their research work as well. We have heard that over 400 participants have registered, and this includes students and teachers. And a special thanks to the Royal Society of Chemistry for associating with this young department of chemistry, Diamond Harbour Women's University. And I wish this web series a grand success for all students, scholars, all speakers. Thank you so much.
Thank you very much, ma'am, for addressing us. As we move further into the inaugural session, may I invite our respected registrar, Dr. Saidur Rahman, to please address us. Please, sir.
Honorable Vice Chancellor, Professor Anuradha Mukhopadhyay, Dean of Science, Professor Sujit Mondol, Coordinator of the Department of Chemistry of our university, teachers, scholars, distinguished guests, resource person, and my dear students. A very good morning to all. I welcome to one of webinar series named International Virtual Symposium on Advances in Chemical Sciences, organized by the Department of Chemistry of Women's University, association with the Royal Society of Chemistry, Department of Chemistry. Thank you for participating in large numbers from different places of the world. This is the second international event organized by the Department of Chemistry in this academic calendar. But this time it is virtual. Students, scholars are engaged in home during this pandemic situation. It will be very good opportunity for them to make virtual interactions with the renowned professors, scholars, scientists from different parts of the world. I hope the lectures of eminent speakers enlighten our students, scholars for their better advancement. I extend my heartiest thanks to all the speakers of the webinar series for giving their kind consent to deliver lecture. I also thank the event organizer, team of Royal Society of Chemistry, for promoting this event. The theme of this symposium is mainly focused on a range of topics in chemical sciences, from material science to chemical biology, from computational chemistry to laboratory-based synthesis of new molecules and their identification by different
I'm afraid there is a slight interruption in the internet connectivity. Dr. Rahman has been disconnected temporarily. So we shall just wait for a few minutes to see if he can join back in. Please bear with us.
Pujarini, I think there is some problem with their connection, so we can move to Professor Mondal. What do you think? Hello.
Yes, Dr. Nondia, I can hear you. Should we proceed then with?
Yeah, I think sure.
Yes, so we'll just wait for sir to see if he can log back in. So may I now invite our respected Dean, Faculty of Science, Professor Shujit Mondal, to please address us. Please, sir.
Thank you very much, Pujarini. Professor Anuradha Mukhopadhyay, the Honorable Vice Chancellor, Diamond Harbour Women's University, Registered Dr. Shaidur Rahman of the university, teachers from various academic departments, research scholars, and students, as well as eminent speakers from different parts of India and abroad. I got delighted when I came to know that the Department of Chemistry, Diamond Harbour Women's University, is going to organize a webinar series, International Virtual Symposium on Advances in Chemical Sciences, in collaboration with Royal Society of Chemistry. I convey my cordial welcome to Royal Society of Chemistry for collaborating with the Department of Chemistry and to organize a mega academic event. I congratulate all the renowned speakers, Professor Devashish Das, Register Calcutta University, Professor Dilip Kumar Maiti, Professor Tapon Kumar Pine, Professor Tapos Chakraborty, Professor Jerome Wasser, Professor Maria Isabel, Professor Devobroto Maiti, Dr. Boulaime Vincent from France, for your supportive gesture and strong cooperation with this webinar series. I must believe that in 3 days, a fruitful discussion will be made between resource persons, teachers, research scholars, and academicians, which will explore new ideas and methodologies as well as knowledges in the field of advances in chemical sciences. The Department of Chemistry of Diamond Harbour Women's University is very young in age. This department is doing well right now. All the faculty members of this department are actively engaged in teaching, research, and organizing this kind of academic programs. I pay my sincere thanks to all of them. This year, in the month of January, the Department of Chemistry organized an international symposium successfully. Again, the department has started to organize an international virtual symposium on advances in chemical sciences. My best wishes are always with all the faculty members of the Department of Chemistry for organizing this kind of academic program frequently. And I hope that 3 days international symposium would be a grand success. Thank you. Thank you all.
Thank you very much, sir, for addressing us. We now are going to invite Mr. Ajit Sharma, who is the General Manager, South Asia Royal Society of Chemistry. Thank you, sir, for associating with us in this webinar. And may I now request you to please address us. Thank you.
Very good morning to you all. So first of all, I am thankful to our Honorable Professor Anuradha, Dr. Rahman, Dr. Nandi, Professor Sujit Mandal, Dr. Pujarini, and the full team of the organizing committee. This is a rare opportunity, and I'm especially thrilled to note that there is a women's university leading the change. And this brings us a refreshing concept in this continuously evolving scenario, where things are changing every day, and in the primarily things where in the scenario where everybody else is doing a lot, it's very hearty to see Diamond University to be a part of that change. And women in science actually is an important part of our continuous engagement with the chemistry community in general, all over the world. So with this, I would like to welcome you all to the International Virtual Symposium on Advances in the Chemical Sciences. It is immense pleasure to be associated with the Diamond Harbour Women's University to organize the symposium. Although the COVID has presented us with a lot of challenges for the students and research area, but it has also democratized some aspects of education. We're able to organize and participate in international conferences as well as listen to eminent scientists being at home. I would like to commend Diamond Harbour University to organize this international meeting and thank Dr. Raj Nandi and Dr. Tanmay Chattopadhyay for RSC Diamond Harbour partnership. For those who aren't familiar with the Royal Society of Chemistry, I will give you a brief introduction about us and our work. So we are a society which was founded back in 1841 in London by a group of scientists, doctors, entrepreneurs, and industrialists. They believed in the power of the chemical science to be the change in this world for the better. To take just one example, our first president, Thomas Graham, invented the life-saving process of dialysis. Over the past 176 years, the RSC has evolved far beyond the scale imagined by our founders. Today, we are a leading global community with 54,000 members in over 100 countries. We are a leading publisher of quality chemical sciences research across the world. And we publish over 34,000 research papers across 45 journals. But we have stayed true to our mission to advance excellence in the chemical sciences for the good of science and of humanity. Now it's very critical for us to understand what is our focus on India. As the oldest continuous chemical society in the world, we are very proud of our heritage. but we are very much focused on the future, and India is the key part of that future. India is already a major center of chemical excellence. It is now the second biggest source of research in RSC journals, and its influence is growing rapidly. We are delighted that Royal Society of Chemistry is the publisher of choice among Indian researchers. We have published over 2,000 research papers in 2019, a significant increase in the recent years. And we very much value India's growing contribution to our journals as authors, reviewers, and editorial board members. We are bringing our flagship and prestigious scientific events to India. And last year, we have organized or associated with over 75 scientific events across this country, advancing the chemical sciences. Through our outreach educational program, Yusuf Hamid Inspirational Chemistry, we have successfully trained 23,000 teachers from about 1,000 schools across 23 states. Over 1,500 economically underprivileged students have participated in the residential Salters chemistry camps, over 20 leading Indian research institutes. And India continues to play an important role in our engagement programs. We are committed to be partnering with Indian scientists to share knowledge with the global science community and to bring UK and Indian scientists together to tackle shared global challenges, including through the Newton Research Links program. And in the last 4 years, we've supported 29 Researcher Links workshops in India on topics that are of vital importance, from the well-being to the developmental sciences, from advances in antimicrobial resistance to developing nanomaterials to tackle water treatment and air pollution. This program has helped to build strong bridges between the UK and the Indian researchers. So without any further ado, I would really appreciate, I am appreciative of this opportunity provided to us by the university. And I really wish all the best to every participant. Please take full advantage of the fantastic content and the speaker lineup that the organizing committee has put up. And I think it will be a great opportunity for all of us to learn some more as we progress in this university. All the best, everyone. Thank you.
Thank you very much, sir, for addressing us. And of course, we are very appreciative of the efforts the Royal Society of Chemistry has made to the chemistry community. And we will be hoping to associate with you even in future for the purpose of science and education. So thank you very much, sir, for taking time out of your schedule to join us. And thank you for associating with us once again. Thank you, sir.
Most welcome. Thank you.
Last but not the least, our coordinator of our department, Dr. Tanmoy Chattopadhyay, is also the secretary of the organizing committee of this webinar, but he hasn't been able to turn up for this session right now because of a prior engagement in a refresher course. So he has been kind to upload a video address to everyone listening to this webinar. So may I request my colleague, Dr. Nandi, to please upload the video.
Respected Honorable Vice Chancellor, Professor Anuradha Mukhopadhyay, Registrar Dr. Muhammad Saidur Rahman, Dean of Science Professor Sujit Mondal, all the speakers, my colleagues, and all the participants. On behalf of Organizing Committee, it is my privilege to propose a vote of thanks speech and acknowledge the contribution of those who worked really hard to make this event happen. Today, we had an opportunity to hear some thoughts, and this will surely be going to enrich our knowledge, enlighten our minds, and have shown us a new path. My gratitude to all the speakers for gracing the occasion and sharing their opinions today. Thank you.
Thank you, Dr. Chattopadhyay. We shall thank all the speakers of the inaugural session once again. And we are now ready to head into the first of our technical sessions. So for this current session, I'm going to hand over the screen to Dr. Nondi. Dr. Nondi, please.
Thank you, Dr. Pujari. So in this technical session, there are two parts. The first part, before lunch break, we have very lucky that we already have the registrar of the University of Calcutta, Professor Debashish Das, and the eminent scientist, Professor Dilip Kumar Baiji. So the first talk will be delivered by the Professor Debashish Das. It is my great honor to have an opportunity to introduce today Professor Debashish Das. Professor Das received his PhD degree from the Indian Association of Cultivation of Science since under the supervision of Professor Nirmalendu Rai Chaudhuri, and in the year of 1996, he pursued his postdoctoral research from National Tsinghua University from Taiwan under the guidance of Professor C.P. Cheng. The Professor Das started his teaching career as an assistant professor at Bangabashi College, and then he moved to the Vishwabharati University as a reader in 2005. In 2008, he joined the University of Calcutta. As a research supervisor, Professor Das is excellent and a very eminent scientist, and the topics of his research are modeling and active sites of the metabolites, bio-inspired catalysis, development of the artificial nucleus, synthesis of nanomaterials using coordination compounds and their application, and etc. He has published more than 125 publications in the international and peer-reviewed reputed journal. 70 scholars have been awarded PhD degree under his supervision. He is the recipient of the different awards. One of them is CRSI Bronze Medal. With this brief introduction, I would like to invite Professor Das to deliver his lecture.
Thank you, Dr. Nondi, for your kind introduction. Good afternoon. Can you hear me?
Yes, sir, you are audible.
Okay, then I can continue. Respected Vice Chancellor ma'am, respected Registrar sir, and respected participants, dignitaries, my dear colleagues, and my dear students. Today I am feeling myself privileged on getting the invitation and getting the honor to share our research activities. I am presenting today the research activities mainly for the students who are now joining in research career, and so that they can understand how we are struggling to do research in university level. So let me allow to start the presentation. So my today's talk, having a title, Small Coordination Complexes as Models of Catechol Oxidase and Phosphatase and as Promising Anti-Inflammatory Agents. Actually, I am a coordination chemist and I am shifting to bioinorganic chemistry. And I strongly believe that life has evolved from inorganic materials, and in that evolution, life has incorporated every facets of inorganic chemistry that was profitable to it. With this particular philosophy, I started my research career in bioinorganic chemistry. In order to understand the chemistry involved in biology, we need to know not only the chemistry of carbon, but also the chemistry of every element. And that is the basis of my research philosophy.
Sir, I'm interrupting. Sorry to interrupt you. Are you sharing your screen?
Yeah, I'm sharing.
I think it's not visible for.
Can you see? Can't you see it?
No, it's not visible. Pujarini, is it visible for you?
I'm presenting, but hello.
Hello, sir. Your slide is not visible.
Yes, I think, sir, the screen has not been shared.
I shared. Okay, I'm doing it again. Is it?
Sir, just press in the present now.
Yeah. Is it?
And then your enter screen.
Okay.
And then select the screen and
Now
then share.
Now you can see it.
No, you have to select the screen. Just press the screen on the screen and then share.
So the screen turns up in the center of your computer screen, and then you have to select that option.
Well, 1 minute. Enter screen.
Then there is a screen window. You have to select, press the window, then share. Yeah, perfect. Thank you.
Fine.
Yeah, fine.
Okay. Okay, this is the title, as I said already. So I'm going to next slide, and I talked on this slide also. Now, all of you know what is model. Model is just a simplified description of a system to assist calculation predictions and to analyze the system. And in bioinorganic chemistry, we have two types of models. One is speculative model and another is corroborative model. Speculative model means when the bio system is not well characterized structurally, then we can think or speculate the structure, and accordingly we may make some model, and that is called the modeling, which is speculative. But when the biosite is well characterized structurally and its function is also known, then we can make some small molecules which will be the representation of that big system. Then it is called corroborative model. And my today's talk is confined with catechol oxidase and phosphatase. So all of you know, when we cut an apple, if we keep it in open atmosphere for a while, it turns brown. What is the reason behind this? Actually, this browning is just due to conversion of this catechol present in apple to quinone. This quinone undergoes autopolymerization, and that autopolymerization actually produce melanin, and that melanin is responsible for this browning. Now, this particular oxidation reaction, two-electron oxidation reaction, is catalyzed by an enzyme known as catechol oxidase. And another one is phosphatase. I will give a brief description later on. And this is the catechol oxidase active site structure. It is a dicopper system reached by OH, and its copper-copper distance is 2.9 angstrom, and it is actually this well characterized biosystem whose structure is known to us. So I am trying to make model of this system. So we have to think about to put two copper center within the distance of 2.9 angstrom. And the silent features of catechol oxidase is that it is a type 3 copper proteins, means there will be two copper centers. And in oxidation state, it will be diamagnetic as antiferromantic couplings going on. And in case of it is deoxy state, it is a copper 1 system, and its catechol oxidase activity is very, very high. It is 8 into 10 to the 6 per hour. It catalyzes exclusively catechol to quinone, and that quinone undergoes autopolymerization to produce the melanin, and that melanin is responsible for the browning of different fruits, etc. And now this catechol oxidase, when we are trying to do some modeling, we need some model substrates. And for modeling of catechol oxidase, we are generally using two model substrates. One is DTBC, 1,3,5-ditertiary butyl catechol, and another is tertiary butyl catechol. The use of 3,5-ditertiary butyl catechol just for the reason that it is readily converted to quinone, and due to presence of two ditertiary butyl group, it will not undergo autopolymerization. So we can study the system very easily, but this tetrachlorocatechol, as you know, it contains electron withdrawing fluoro groups, so it is very hard to oxidize. So if in your system is very active, then that can only oxidize this tetrachlorocatechol, not the other system. And generally, solvent used in particular study is methanol and acetonitrile, and we can perform this study by using UV spectrophotometer as the basic instrument. Now, if you look at the catechol, then we will find that 1 minute, please. I have a
Hello, sir. You are not audible. I think you stopped. Hello. Hello. Dr. Pujarini, are you here?
Yes, Dr. Nandi.
Is it audible?
No, I'm not getting any sound here.
Okay.
Only the screen is visible.
hello.
Yeah, sir. You are audible now.
You hear me?
Yes.
Yeah, sir. Audible. Thank you.
Please go ahead.
This disturbance is going on.
Yeah, you can continue, sir.
And this catechol has several binding modes, as I'm showing in this slide. And the possible mechanistic pathway has also been proposed by two eminent research groups. One is Krebs and one is Solomon. But on the basis of some speculation, there were no experimental evidences in favor of any of the intermediates in favor of the binding modes. One group is thinking about monodentate coordination mode. One group is thinking about bidentate coordination mode. So what is the actual coordination mode? Not yet settled. So we started our journey with those questions. What will be the binding mode? In which way it is actually going on? What will be intermediates, etc., etc. And we tried to make the models with a simple ligand system. Our ligand systems are chip-based ligand, reduced chip-based ligand, and manning-based ligand. And our metal ions of interest are copper, nickel, manganese, cobalt, and zinc. And our queries are mode of coordination of catechol and the structure of the adduct, relation between electrochemical property and catechols activity, metal substitution effect. Just if we substitute copper by other metals, what will be the activity? And what are the different factors on which catechols activity will depend, and possible mechanism for catechols activity of synthesized models, and metal center redox participation or metal radical pathway. So we will try to answer all those queries. So let's start with a dinuclear copper 2 system. Our ligand system, as I told you, it is simple chip-based ligand. And with the chip-based ligand, we prepare the complexes. And whether the complex is formed or not, that you have to assign by single crystal X-ray analysis. And from the single crystal X-ray analysis, we are very much sure that the copper-copper distance in this particular case is 2.97 angstrom. And if you look at the piperazine nitrogen, the nitrogen is protonated. And so this is another important factor. The other complexes are also characterized by similar way. We have the octave views with copper-copper distance within the limit of 2.9 angstrom. As I told you, that this is the particular requirement. And in this particular case, it is cover distance is near 3.1 angstrom. So all these complexes which we have synthesized follow the basic trend, that is the copper-copper distance is maintaining within the limit of 2.9 angstrom. So they could be the model of critical oxidation. So what is going on if we take 3,5 ditertiary catechol and convert it to its corresponding quinone? How we can understand the quinone is forming? That can be understandable from this invisible spectral study. Actually, 3,5 BQ will exhibit lambda max as near about 400 nanometer. And when it is tertiary butyl tetrachlorocatechol, then it will exhibit lambda max at 437 nanometer. So with this basic data, we have started our reactions with our complexes. So this complex exhibits a lambda max at near about 350 nanometer. And when we add 3,5 ditertiary butyl catechol, which has no signature within the range of 300 to 500 nanometer, we are getting one band at near about 450 nanometer. And with time, this particular band decreases with concomitant increment of the band at 350 nanometer. But as I said, if it is the catalyst which oxidized the 3,5 ditertiary butyl catechol to corresponding quinone, then it should exhibit a lambda max at 400 nanometer, but we are not getting that. So what is going on? Then we may think about these two bands. First, for representing two important pieces, and they may be the intermediates. And then we extended our reaction time, and with after 6 hours, what we observed, just to look at these particular changes, after 6 hours, we are getting a band centered at 400 nanometer. This is the signature of formation of 3,5 ditertiary quinone. So this oxidation reaction catalyzed by our complex proceeds through two intermediates, ES1 and ES2. It is now experimentally verified. Now we have to characterize, when we apply other catalysts, we are getting the similar trend. So we are not going in details on in each case. Now we have to characterize the intermediates, which are ES1 and which is ES2 by ESIM study. From the ESIM study, these are the proposed structures of ES1 and ES2. 1B corresponds to ES1, where it is monodentate mode of coordination of catechol, and ES2, it is bidentate mode of coordination, as is proposed by Solomon and Krebs. But they have no experimental evidences. Now we have. So ES1 from ESIM study looks that it is justified that the structure is monodentate mode of coordination is there, and when it is ES2 bidentate mode of coordination, we characterize it by ESIM study. Now, just we change the solvent from acetonitrile to methanol. With the same complex 1, we are not getting any intermediates. So what is the reason, or what is going on here? Actually, from this perspective, it is not possible to say that this reaction doesn't proceed with the formation of ES1 or ES2, something like that. Maybe our time limit which we are applying in the spectral study is not quite good enough to characterize the two intermediates, but there is a simple conversion of 3,5 DTBC to 3,5 DTBC, which is changing the solvent from acetonitrile to methanol. So these are the similar trend we are getting from other complexes. And since it's simple conversion from one starting material 3,5 DTBC to DTBQ is going on in methanol medium, we can apply kinetics here. And here we are getting the K catalyst value is 3 into 10 to the power 4 per hour in case of complex 1. But in case of catechol oxidase, as I told you, it is 8 into 10 to the 6 per hour. So our catalyst is good enough, but not at all comparable to our natural system. And interestingly, since our complex 1 is very active, whether its activity is good enough to catalyze TCC to TCQ, we perform the experiment, and from this spectral study, you will understand that our for complex 1 is respectful catalyst, which can catalyze even TCC to TCQ. Now we extended our idea to other dinuclear systems, and in case, as I told you till now, it is macroacyclic system. Now we are making macrocyclic system of this kind, and try to understand whether the system will be more interesting or more comparable to the natural system or not. And our studies clearly shows that mononuclear system, these are the octave views, where copper-copper distance is within a limit of 3 angstrom. So they may use as a model system, and these are the octave views. And when in easy visible spectrum we are performing in accidental medium, in this case we are not getting any intermediate. So when it is macroacyclic system, in accidental medium we are getting intermediates, but in macrocyclic system we are not getting that one. So this is also another interesting observation, and it is a simple conversion of critical to quinone without formation of any intermediates. And in accidental medium, the activity is completely very low. So in this case, actually activity is not going on due to formation of the adduct, and these adducts are very stable and it is not undergoing further oxidation. And we also perform the kinetics, only it is 3 times lesser active in case of, in compared to our macrocyclic system. And we are also performing what is the reason behind the activity orders. And in this case, activity of 2 is the lowest and activity of 5 is the highest. And that can be analyzed by considering the electronic and scale factors. And I am not going in details, but this is the conclusion. The 6-membered ring exhibits better activity than 5-membered counterparts, and the catalytic efficiency of 5-membered Tourette ring complexes are observed to influence by steric demand rather than electronic factors. Now, another interesting observation or thinking we have to address, that is the conversion of catechol to quinone is a 2-electron oxidation process. Since it is a 2-electron oxidation process, the electrochemical property of the catalytic site, that is the copper system, must have influence on the catalytic activity. Now, how they are correlated? That is what will be the relation between the catalytic efficiency and its electrochemical behavior. That is our next point to address. And before to start this particular topic, I must say that Krebs, who is the pioneer in this field, in his one classical paper published in Dalton Transactions, they wrote no clear relationship between the electrochemical properties of the complexes and the reported data for 3,5-DTBC exists. It may be that the poorly defined redox chemistry of this class of complexes will never allow such a correlation to be established. But still, we think that there must be a correlation. That's why we prepared as many as 15 complexes. We characterize all 15 complexes by accessing with the structure analysis. These are the structural representation. And we then perform the electrochemical study with those complexes, both CB and DPV. These are the CBs and DPV studies, and we make the table. So we have now electrochemical property of all of our 15 complexes, and then we perform their catalytic activity, and from that we also determine the K catalyst value. Now we have K catalyst value and we have E0 value. Now, if we now compare, then we should get some idea. But interestingly, we fail to get any correlation. And then we thought there may be some, we are wrong, our conception is wrong, and Krebs was right. But at that stage, we realized that we are just comparing the electrochemical property of the complex with the catalyst in absence of the catalyst. So, electrochemical property of the complexes in absence of the substrate. So, when the substrate is binding, the structure of the catalyst will change. And as you know, the structural change will have profound influence on the E0 values. So we should consider the E0 value of the catalyst when the substrate binds to the catalyst system. And we also, from our experiments, we realized that yes, when substrate binds with the catalyst, E0 value changes. But we observed it with complex 1. We failed to get experimental data with others, so we performed theoretical study. From theoretical study, we calculated the energy associated with this particular transformations, particularly this copper 2 system to copper 1 system. What will be the energy associated with this particular step? And this we calculated by applying theoretical calculations. And we have now the energy associated for the conversion of this 2 to 1 conversion, and we have the catalyst value which we have determined earlier. When we just make a relation, we are getting very good straight line. That implies lower the energy required for the conversion of copper 2 to copper 1 system, higher will be the activity. And there's energy actually associated with the E0 value. So there is a good correlation between E0 value and the catalytic activity. Now we are thinking about what will happen if copper system is replaced by manganese system. And for this metal substitution effect to study, we performed several, we synthesized several manganese complexes. All are macroacyclic type, both mononuclear and dinuclear. And these mononuclear and dinuclear complexes then use to as catalyst. And from the invisible study, we realized that all complexes are good catalysts to convert catechol to PE. But these mononuclear complexes, when it is binuclear complexes, the activity is no activity we are finding in methanol medium. We perform the same catalytic system in accidental medium, and we are getting here also some intermediates, and the activity is not good enough as we observed in case of copper system. These manganese systems are less active in compared to copper system, and that gives us a clue why nature selected copper instead of manganese, although manganese is also a redox active system. So we have the conclusion of mononuclear manganese complexes are active in both methanol acetyl medium, but dinuclear complexes are active in acetyl medium but inactive in methanol medium. Now here is the most important questions which we answered. That is, what is the reason behind this catalytic activity? We have manganese 3 system, so it is EPR inactive. So when we will take the EPR spectrum of manganese complexes, there is no peak. When we mix our substrate and take the EPR spectrum, intensive gas 6-line EPR, which is corresponding to formation of manganese 2. So this particular experiment clearly demonstrates that 3,5 DTBC conversion in presence of oxygen when our complex manganese 3 is acting as catalyst, its oxidation is going through reduction of manganese 2 to manganese 3 to manganese 2. So here also metal center redox participation is responsible for the catalytic activity. We extended our reaction in manganese 2 system. Manganese 2 system also showing catalytic activity. Now question comes whether manganese 2 reduction to manganese 1 is possible or not. That will be answered later on. And these are the manganese 2 system. So when the manganese 2 system we are preparing, our ligand system is different in compared to manganese 3. And here also our activity is much lower than case of manganese 3. So manganese 3 is better catalyst than manganese 2. Now question may come for manganese system, whether the manganese system itself, that is we are using manganese 2 as the salt, itself acting as catalyst or not. But from this spectral study, it is clear that manganese 2 system has no catalytic activity. Now we move to nickel system. It is generally not considered as active, as electrochemically active. It is redox innocent we can think about. Still, whether it is showing activity or not, we prepare a dinuclear nickel system with the same ligand system as we prepared with the dicopper system, complex one I demonstrated in the first slide. Here also this piperazine nitrogen is photometric. This particular phenomena is very important in catalytic activity. I will let you know later on. Here also nickel-nickel distance is 2.9 angstrom as is necessary for a catalytic activity study. And in this case, whenever we are using 3,5 DTBC, we are getting 3,5 DT2 very easily. And when the system we are using acetonitrile as medium, we are getting one intermediate, that is ES1, that is a monodentate mode of fashion, monodentate mode of coordination is going on, but we fail to get ES2. So now we just think about whether this structure of ES1 or ES2 is similar as in case of copper 2 system or not. We propose two systems, that is one is 1C and 1B. And we characterize the way that actually going on in system through ESIM study. And from ESIM study, we are very sure that the 1C is the most probable intermediate in case of nickel to catalyzed catechol oxidation. But from this study, we fail to understand whether the nickel system is performing its activity through metal-centered redox participation or through another pathway. In order to understand that particular issue, we extended our study and we prepared several dinuclear nickel-2 systems, nickel-2 complexes, and used them as catalyst. And in this case, we are getting very good activity. And then we extended our experimental studies with cyclic voltammetry study and EPR study. In EPR study, we are getting one band at G is equal to near about 2 that indicates the formation of one radical. And but in this case, our CP is not good enough and I'll give any clue whether nickel is converting to nickel 2 to nickel 1, and that is the reason for the oxidation or not. But this from EPR study, we are getting a clue that there is the possibility of formation of some radical. And I will discuss in details in case of gene system. That is this particular gene system. One may think about that is in case of nickel, there is a possibility of metal-centered redox participation. But gene 2 is unambiguously a redox innocent system. So if this gene 2 system can show activity, then we must think about the possibility of redox radical pathways instead of redox participation. So we prepared several gene complexes with these shift-based ligands and characterize them as usual, and they are showing very interesting catechol activity. We were amazed that gene 2 systems are also showing activity. Now here we are thinking about why gene system is showing the activity, and when we just add gene complex with gene is totally EPR innocent, there will be no peak in EPR study. But when we add substrate, we are getting a peak at G is equal to 2, with one peak at that is at a half peak we are getting at long distance, and that this particular small peak gives us a clue that there is another radical, that is there is two radicals widely separated from each other. There is no coupling. So radical formation is going on. It is unambiguously verified. And we also performed the cyclic voltammetry study, and in this case, gene 2 should not exhibit any peak, but we are getting the peak just due to formation of the radicals. And we also applied the theoretical calculations. From the theoretical calculations, we are very sure that there is a formation of one radical at the ligand periphery, not in the metal center. So as a whole, we are now in a position to give to propose the possible mechanism through which our gene system is showing the activity. And this particular mechanistic pathway clearly shows that there is the formation of imine radical, and that imine radical, we are for this imine radical, when it is forming, we are getting also one semi-benzoquinone radical. As I told you in the last slide, in EPR spectrum, we are getting 2 peaks. and that two peaks shows that there is formation of two radicals which are not well connected, they are wide separated. And from this, we are proposing this mechanism to justify our EPR spectral study. So from this particular system, we are now at the position to tell unambiguously that in case of catechol oxidase study, there is a possibility of radical pathway instead of metal center redox participation. We now extended that idea with manning-based ligands. We prepared several manning-based ligands and their complexes and characterize them by usual ways. And in this particular, from this particular slide, if you look at carefully, then we are getting a peak at 405 nanometer. That is the signature of formation of 35DT-BQ. But in addition, we are getting two peaks at 575 nanometer and 285 nanometer. That invariably proves that there is the formation of some radical, which is actually phenoxy-free radical. And this manic-based system, there is no possibility of imine radical formation. Still, it is showing the activity, and that activity is due to phenoxy-free radical formation. And we analyzed their activity study and also their catechol rate of reactions, etc. And whether when we compare the activity of mono and dinuclear systems, we realize that dinuclear system is less active than mononuclear system. And we explained that lower activity of dinuclear system by EPR study. When we mix the dinuclear system with our substrate, two radicals actually are forming, two phenoxy radicals. And the two phenoxy radicals with time they merge and we making a the radical converted to bond. And so this radical is not responsible or is not able to take part in oxidation process. As a result, with time, the dinuclear complexes show lesser activity, but we have a mononuclear complexes show higher activity. And we also extended with cobalt system. In cobalt system also we are getting activity. So all metal ions which we have taken into account are showing catechol as activity, but copper system is the best one. And that's why copper system is actually taken by natural system for their activity. And follow the EPR study from which we are sure that radical pathway is also an alternative in addition to active center redox participation of the metal center. And we are now moving to dinuclear cobalt systems. Dinuclear cobalt systems like mononuclear systems are also showing activity. And we now look at this reduced shift-based ligand system. We are just taking the same shift-based ligand and making their we converted them to corresponding reduced shift-based ligand to understand whether shift-based complexes is more active or reduced shift-based complex, and what is the mechanism involved in shift-based complex catalyzed reaction, and what is the mechanism involved in reduced shift-based catalyzed reactions. So for this, these are the ligand systems. This is the complex one which I am showing here. It is shift-based complex. We converted them into reduced shift-based complex. Their structure also will characterized by accessing crystal analysis, and both of them are showing activity but with a different degree. And the EPR study, from the EPR study, we are very sure that in case of complex 1, that is the shift-based complex, the activity is just due to formation of the imine radical. But when it is complex 2, there is no possibility of formation of imine radical because it is amine system. It is reduced shift-based. But still, we are getting activity, and this activity, if you look at the EPR spectrum, we are getting different kind of EPR spectrum. And compared to the complex 1 catalyzed reactions, we should get 4 bands, but we are getting actually 3 bands with the middle band actually a combination of 2 bands. So here another radical formation is going on, that is adding radical, and accordingly we have proposed this particular mechanism through which the reduced shift-based nickel complexes is acting as catalyst. Now, we have dinuclear nickel systems, but what will happen if we convert to mononuclear nickel systems? And for this, we have taken very simple ligand system, the salicylic with piperazine ligand, and we are making just three complexes, one with three different halides, chloride, bromide, and iodide. And we characterize all those complexes by single crystal assay analysis. If we look at the crystal structure, we will find a similar structure. That is, the nickel is octahedral nickel complex with two halide at the outside of the that is the counter anion, and ligand metal system contains three water molecules. So actual structure they are very same. But whenever we perform their activity study, we are amazed that complex 1 and complex 2, that is the bromo and iodo complex, that is complex 1 and complex 2, bromo and iodo complex are active. But what about chloro complex? Whenever it is chloro complex, there is no activity. So this is very funny that their structure, solid state structure is very same, but their activity are very different. And in order to understand what is the reason behind this different behavior, we performed the age-old conductivity study. That is that particular experimental study which helps learners to establish coordination chemistry. And when we just taken the complex 1, 2, and 3 and performed their conductivity study, it is 1:2 electrolyte. But in case of complex fluorocomplex, what is going on? It's converted to 1:1 electrolyte, and we represented that particular behavior from this way. That is, when it is fluorocomplex, when it is in solution, one water molecule is replaced by anation, and since chlorine attachment takes place with the nickel system, nickel lost its formal positive 2 charge, and as a result, it has less affinity to take in association with the 3,5-DTBC, which is the negatively charged. So first and foremost reason for activity is the interaction between catalyst and the substrate. For this particular species, this particular phenomena is not going on, and as a result, it is inactive. And this is very interesting observation we observed during our study. And here also we realized that the activity exhibited by bromo and iodo complexes are due to radical formation. Hello. We took the assistance of DFT calculation to corroborate our experimental evidences, and just look at the conversion of these eco-complex annotated complexes, that is chlorine addition takes place in the nickel system, and that is fundamentally possible. And in other cases, it is not fundamentally possible. That's why in case of chlorocomplexes, actually annation takes place. And we also performed that other way that radical formation is going on or not, like this string density calculation. We are very sure that there is a radical formation at the periphery of the ligand. So this is the proposed mechanism through which our mononuclear system showing their activity, and I already discussed why it is not showing activity in other cases. It extended our this idea whether we can apply we can convert mononuclear trinuclear like that if we are pentanuclear complexes, and these pentanuclear nickel complexes are also showing very good activity. In this particular case also, the activity is not due to methyl redox participation, but due to the radical participation. Now we move to another part of my talk. That is this phosphate is phosphate as a very important biomolecule in our system. It is present in ATP, DNA, RNA, etc. And if this bond cleavage doesn't take place, we will not get the energy. And for this reason, phosphatase activity is very fundamental and very important biological processes. And the metal center which is involved in this catalytic system is gene. Now, whether we can make some models of these particular biocides and try to understand how it is effective the mechanism of these reactions are going on. And this is the thing, as you know, is the most second most abundant trace element, and it will make so many biological metallobiocides are associated with the gene system. So this is the first thing. In order to understand the phosphatase activity or not, system is from nitrocyanil phosphate disodium salt, and this salt is inactive. But when it's converted to 4-nitrophenolate, it shows a band at 400 to 439. And just why I am talking about this one. In case of critical oxygen, just we will do spectrophotometer of the basic instrument. We have taken another activity study, that is the phosphatase activity. Here also the individual spectrophotometer will be our basic instrument, whether our catalyst is active. This is our gene system with some shift-based ligands, very simple shift-based ligands, and just look at the amine part. We have changed 2 carbon to 3 carbon system, and with changing 1 carbon, we are getting different structural property. That is, from 3 carbon we are getting mononuclear complex 2, and with 2, that is, we are getting trinuclear complexes. So just backbone change of the ligand system may change a lot in the total system. And this we have now trinuclear and mononuclear system, and we have applied them to study their activity and whether why not just come to the same point, why not this particular system converting that is the when we have propyl system, why we are not getting trinuclear complex, and when it is ethylene, why we are not getting dinuclear system. Not to understand, we perform this DFT study, and from the DFT study it is clear that energetics is the responsible for not converting tri in case of propylene group, and in case of ethylene group it is not normal. Both of them are showing activity, but complex 1 is much more active. That is, the trinuclear complex is more active than the mononuclear complex. And why trinuclear complex is more active than mononuclear complex, we again take the assistance of DFT study. Just look at the first step. The first step in case of trinuclear complex, the delta E3 is minus 5.9 kilocalorie per mole. But the similar step in case of mononuclear complex, that is delta E6, it is plus 6.7. That particular thermodynamic data give us the clue why trinuclear complex is more active than mononuclear complex. Now we started our activity with study with gene 2 complexes based on Manning base. This Manning base we prepared, and from the mononucleating system we have got dinuclear complex, and with dinucleating ligand system we are getting mononuclear complex. That is also interesting observation. And why in case of with the dinuclear system we are getting mononuclear complex, that we explained from the crystallographic study as well as theoretical study, that this particular amine is protonated. And since it is protonated, this lone pair is no longer available for making bond with the incoming gene system, and so it is forming mononuclear complex. So with mononucleating ligand, we are getting dinuclear complex, and dinuclear ligand, we are getting mononuclear complex. Their crystal structure is now with us, and both of them are showing good activity. We are getting band at 400 nanometer in both cases, and their activity, we have correlated their activity. I mean, compared to the dinuclear complex, the mononuclear dinuclear complex is more active, and it is near about 2 times active. So we may think about why it is 2 times active. Actually, 2 times activity is just due to conversion of this dinuclear complex in solution system to mononuclear complex. Now, why we are thinking about phosphatase activity study? Actually, our motto is not only to understand what activity is going on or not, but our main focus is to think about whether we can apply our synthesis complexes for the benefit of the management. If all of you know that the DNA is, actually we are focusing on the cancer. So cancer is the uncontrolled growth of cell, and the cell growth is just due to the replication of this DNA. So we can, if we can stop the DNA, then synthesis, then we can stop the cancer. It is all of you know. But how we can stop that? For there's several ways we can stop the replications. One of the way is to stop the hydrogen bond. One of the way is to stop the hydrolysis of the phosphate bond. So our thinking is that if our complexes are showing active phosphatase activity, the phosphoester bond cleavage is going on by our complexes, and, then it is possible that our complex may terminate the cell growth. And how we can study whether our complexes are acting on DNA. And for this, all of you know that DNA, three forms have, that is the form 1, form 2, and form 3. And from the gel electrolysis study, we can understand whether our complexes is acting on the DNA or not. Just look at this particular system. Here, our ligand system is contains one amine part. There is no two diamine. It is not diamine system. So if our aldehyde contains two aldehyde, then there is a possibility of formation of this kind of macroacyclic system. But with our surprise, when we observe the crystal structure, we realize that this system making a macrocyclic system. And this macrocyclic system with oxazolidine and oxazine side chain. And if you look at the structures carefully, you will find 4 chiral centers. So it is really fantastic synthetic system. And it is, there is no credit of us. It is natural system. If you just take, we are fortunate enough to choose the particular ligands, and we are getting macroacyclic system, a macrocyclic system with oxazolidine and oxazine side rings, exocyclic side ring with 4 chiral centers. These are the views of our complexes. What we are talking about, that if our complex can show your activity on DNA cleavage, then this particular experiment gives us the idea whether our complex is acting as DNA cleavager or not. Form 1, that is the plasmid DNA. If when our the lane 1 shows there is no addition of our catalyst, we are gradually adding our catalyst concentration from 20, 40, 80, 160 micromolar. That is gradually increasing our concentration of the catalyst. And what is our observation? You see at the last one, that is there is nearly no form 1. That is converted to form 2. That is the total meeting. That is the rupturing of the total DNA system. So our catalyst can rupture the DNA. But it is, if we can apply it for abnormal DNA, then it is beneficial. But if it is normal DNA, then it is, there is no meaning. Actually, it is. So we have to study the cytotoxicity effect. And the cytotoxicity effect, whether it is, if it is past the cytotoxicity effect, then there is a possibility of using them as an anti-cancer agent. This particular, we apply the complex in cell line also, and this from the A represents the cancer cell, AGS cancer cell line. And when we use our complex in this system, cell proliferation stops. That implies our complex has the profound efficiency to work on cancer cell lines. And these are the MPT assay. From the MPT assay also, we realized our complex 3, that is, complex 3 is a very promising one. We can extend our study in later on. to understand whether it is promising or not. And in present days, we are now thinking about whether we can extend our idea or knowledge in coordination polymers. And we have synthesized a few coordination polymers using this terephthalic acid as the linker, as the holder, and this particular different diamine system as the linker. And we have the structural differences, morphological, topological differences on changing the linker system. I'm not going in details. These are the different structure analysis system. But what is important, what I want to discuss is that we prepared the coordination polymers, but they are large in size. We cannot apply it in cell biological systems, because until and unless the system's size is 100 nanometer, it cannot penetrate the cell. So what we apply here, we just converted our synthesized nanomaterials into synthesized coordination polymers into nanomaterials by hand grinding. And whether the structural integrity is maintained or not, we perform the PXRD. And from the PXRD, it is very clear that our structural integrity is maintained, and we apply them in cell membrane biological study. From this scratch experiment, it is if you look at the LEN2, that is this one. In LEN2, after 24 hours, there is no cell propagation, so it clearly shows our nanomaterials, which we synthesized by hand grinding from synthesized coordination polymers, are interesting in case of cancer activity study. And in order to understand whether what is the mechanism through which it is performing, we perform the immunofluorescence study. And from the immunofluorescence study, we get an idea that mitochondrial dependent apoptosis is responsible for the activity of our study. So now I'm in the last slide. Only what we can do, we have to study more, learn more, so that we will, can apply our knowledge, and that knowledge, if we from accumulated knowledge, someday we may make some breakthrough. And now it is the time of acknowledgement. First of all, my institute, Department of Chemistry, University of Calcutta, and I am here just for my students, and I am presenting here all the activities done by my students. These are my students, and of course, without collaboration, our study is not possible from university. So these are my collaborators, and as well as financial assistants are very much prepared. Thank you so much for your kind introduction, kind patience.
Thank you, sir, for your nice presentation. I hope the participants have learned many things from your talk, and it's really good presentation. There are many questions in the YouTube link and chat box. I want to take something from. There's a question from Preeti Karmakar. In DFT studies, which method and which basis set have been used?
Frankly speaking, for the DFT study, we need the assistance of collaborator, and that's why I'm not an expert in this particular field. I am a coordination chemist, so I can answer the coordination part more clearly, and that's why I acknowledge my collaborators.
Okay, sir. Thank you. So one of our students, Orkita Datta, she is asking that what will happen if we substitute the copper complex with the corresponding rhodium complexes?
Actually, we didn't take rhodium or 4D or 5D elements or lanthanides just for the reason that they are not bio-relevant. And in case of rhodium complex, it will be very active. No question at all, because they are highly redox active.
Okay. So there are a few questions. So I want to take one or two in front of you. What are the factors responsible for the nucleophilic attack of water or hydroxo or phosphorus center?
Yes, that is an important question for phosphorus activity. I failed to show you that slides. Is if until and unless your system contains some water, basically coordinated water, there is a less possibility of using this complex as catalyst for phosphorus activity. And so you have to get that particular metal center must have the affinity to bond with water molecules. That is the prerequisite, and at the same time, your phosphorus nucleophilicity is also very important in activity.
Okay. So one last question is, does the catechol activity influenced by the nuclearity of complexes?
So far as our study concerned, nuclearity, if we think about in copper system, it is dicopper is the most active, and monocopper near less active, and the distance is very important. If copper-copper distance, it is dinuclear, and copper-copper distance is more than 4 angstrom. There is nearly no activity, although some people has been reported some activity with those systems. But the most crucial part is that we have to make a system which is very close to the natural system.
Okay, sir. So thank you, sir, for your explanation and for being with us. Yeah, thank you, sir. So now we can proceed for our next lecture. So our next technical session will be delivered by Professor Dilip Kumar Maiti. Sir, are you here?
Yes, yes.
Okay, sir.
Raj, proceed.
Okay, thank you. Sir, Professor Dash, would you kindly? Okay, it's fine. Thank you. So we can start our next lecture. So Professor, our next lecture will be delivered by Professor Dilip Kumar Dash as a professor of Department of Chemistry, Calcutta University. It is my great pleasure to introduce Professor Dilip Kumar Dash, who has awarded his PhD in 1998 from Indian Institute of Chemical Biology and Jadavpur University. His thesis work was on the stereoselective synthesis. After his PhD, he did some industrial work in RPG Life Sciences Limited in Mumbai and Shiva India Private Limited. And then he started his teaching career in Damkal College, Basantpur in 2000. He gathered his postdoctoral experience from School of Medicine, Wayne State of University, USA, and also in the Jadavpur University. So he became full professor in 2019. More than 37 PhD scholars completed PhD under his guidance, and more than 33 postdoctoral researchers have worked with him. A dynamic personality like him could not be only academic. He recognized number of international symposiums which have been definitely enriched the Indian science. He recognized the Nobel laureate lecture by Nobel laureate Professor Ishi Negisi, and also he is a founder of Ashima Chatterjee Foundation, and he already organized a big event, international symposium in the memory of Ashima Chatterjee in Heritage Institute of Kolkata. So Professor Dilip Kumar Maiti received many awards. Few of them is he's a fellow of Royal Society of Chemistry, and he is a fellow of Indian Chemical Society. He received many awards, and few of them are Vasudev Banerjee Memorial Award, Indian Chemical Society Award, Professor Satyashiv Sarkar Endowment Award. So with this brief introduction, I would like to invite Professor Dilip Kumar Maiti to deliver his talk. Sir.
Okay. Give me a few minutes. It's not...
Okay. So just with your permission, can you record your talk?
Yeah, sure.
Okay, thank you. Sir, are you using two devices?
No, this presentation is not working. I don't know.
You can press the present now.
Can you press from there?
You are already presenting, sir. So
Yeah,
just
but
I think you already put presentation in one device and trying to just press. You have to deactivate the present now in your mobile and activate the present now on your laptop. Hello, sir. Can you hear me? Professor Maiti? Participant, just give few minutes for there is some technical issue. We'll be back soon when the Professor Maiti will join again. Sir, now it's visible. Can you hear me? Professor Maiti, you are not audible. Okay, sir. Now you are audible.
Yeah.
So,
Very good afternoon.
present.
May I audible?
Yes, sir. You are audible and visible. Your slides are pretty visible. You can start, sir.
Hello. Excellent. Okay, very good afternoon. First of all, I would like to thank Dr. Raj and all the organizer of Diamond Harbour Women's University. Today, I'm going to talk on innovative organic material sensor, organic nanoelectronic devices. As we basically, my group work on organic synthesis and in the diverse field, and also we work in material and devices. Preliminarily, I'll talk a little bit about what is nanoscience, because most of the students may not know about nanoscience. So slowly I'll go through that and then I'll enter to our work so that you can understand all these things. Nano came from the nanos, a Greek word that is means actually 1 billionth of a meter, means dwarf, it is 1 billionth of a meter. And nanoscience is very interesting in that sense. Our ancestors divided science, technology, then science, chemistry, physics, mathematics, and then chemistry having 4 groups, you know that. But nanoscience is a single platform where all the people from chemistry, physics, mathematics, and material, electronics, engineering, they are working together. Something great and with very small things. Okay, so what is nano? Nano means it is any particle having at least one dimension. If it is 1 to 100 nanometer, it is called nanomaterial. But nanomaterial is completely different than other particles. As you can see, that if you want to shoot a particle, you need a gun and you need a bullet. As you can see in this cartoon, is where nanoparticles are there, but these angry men need a high resolution camera. The reason is very simple. Nanoparticle cannot be seen with your naked eye. You need a high resolution camera to see that one, then only you can see. And you can see in the left side, there is a common platform or diagram for imaging nanomaterials. Means you cannot see nanomaterial with your naked eyes, but when it is in the SEM, TM, XM, AFM, then you can see this nanomaterial on that. Okay, Richard Feynman actually called father of the nanoscience and nanotechnology. In 1959, he told there is a plenty of room in the bottom. You can write 5 volume of Britannica in the tip of a pin. So in the tip of a pin means you can write 5 volume of dictionary over there. But the problem is you cannot see with your naked eye. And then he told that when everyone asked him, he told that you need to improve the resolution of your camera under 100 times, and then only you can see that one. Nanoparticle actually it is already there. It was there. As you can see a letter from Benjamin Franklin. He wrote a letter to the William Brownrigg around more than 200 years ago. And he observed this phenomena. I can see this. This is the phenomena he observed. He put a spoon of oil on the water, and he observed that it is spread out almost 1 acre. But ultimately, it looks very smooth and looks like a glass. Actually, what happened? Oil is not miscible in water, so it remains on the surface of water in the pond. So it's spreading out. It's spread out only that region when it forms a nanoparticle. Because oil, is not soluble in water, so oil molecule, you know, it has a long chain hydrocarbon. So basically it will come together and it will give you this particular nanoparticle, and when it forms a nanoparticle, it is become color, because even the material is colorless, but when it will form nanomaterial, it will give you color according to size, shape, and dimension. Okay, so let's try to understand what is nano, how it looks. So we usually, smallest thing we watch our hair. As you can see here, if you really watch, that is also 100,000 times greater than a nanometer. And if you have here, you put a red blood cell and you have observed in microscope in BSc classes like biology and other classes. And it is observed that the red blood cell also like 6,000 nanometer, means 6,000 greater than, size greater than the nanometer. And in DNA, especially DNA, RNA or protein, having the dimension is, this length is, when it is small, then it is actually in the nano range. So you know that biological reaction is going on in our body, and all biological reaction may be performed by this nanoparticle, and that's why this chemical transformation can easily be done in our body using nanomaterial, and the nanomaterial functioning very well at this nano level. Okay, let's give you a few examples that to understand that how nanoparticle can be used. So here, suppose you have a big building and you want to paint that particular building with your with a paint. It is very difficult to do that every year and to clean and this thing. But if you use small amount of titania basically titanium nanoparticle, it is actually titanium oxide. So with the paint, and then you paint that particular building first time, and in 20 years you no need to climb up and clean that. Then what is happening? It is very simple. Titanium oxide, you know that sunlight having small amount of ultraviolet radiation. So titanium oxide become activated using ultraviolet radiation in the daytime, and it break down the all carbon-carbon bond in the oil. Basically, what is chipping on that particular color or of that particular building, that is nothing but inorganic metal oxide, metal oxide, and oil. So when breakdown of this oil, carbon-carbon bond is taken place to alcohol, then aldehyde, then carbon dioxide. So that inorganic material become loosely bound, it will blow down, or when rain will come, it will wash out, and your building will be clear. Okay, so suppose you purchase a car, and usually there is a big fight in your house. What should be the color? Now the technology, nanotechnology is said that if you can use different nanoparticle, you can use with the paint, and you can use that one, and then you can apply those compound, and this color, you may morning you can get one particle will give you yellow color, and the daytime, in the noon time, it can give you blue color. In the afternoon, it can give you sky color, and in the night, it can give you black color. So these are the nanoscience and nanotechnology that beautifully come in our changing in our life with the future. Means it is okay. So this is another thing very interesting, that in medical scenario also it will be very useful. It will be very useful that someone suffering from cancer, suppose in stomach or in heart. So how can you are having drug, how can you transfer that particular drug to that particular organ? Because that drug is very toxic. You cannot send to all over your body to that one. Then how can you do that? So it can be done by nanotube. This very small needle, you cannot see with the naked eye, and it can enter and reach to that particular organ and transfer this all drug. Drug delivery can be done very easily. Now you can ask that how can you send this, that will be whole, even it is so small, even cell cannot understand that something is going inside. So that's the beauty of nanoparticle. You can see over now one disease is neuro disease is very difficult to understand. And you can see one snail just took birth, very small, maybe 1 millimeter by 1 millimeter or 1 millimeter radius like that. And nano device is made so that all this, you know, that chemical reaction is done in the neuro system. And according to that, neurotransmitter go and bind to the receptor and give the response. So this type of response actually moves through electric impulse and electric impulse. So that's why it happens. So it happens like that. So all this information actually gathered, taken by this nanomaterial and telling us that how this chemical transformation is going on, and this transformation transforming to the electric wave, and that electric impulse actually create all this nervous system to make it easy in our life. Okay, so with this prospect of nanomaterial, let's see that how nanomaterial actually can we make. Now you can see this nanomaterial, gold having golden color. When you have a atom, this colorless. But when you have around 1 nanometer, so that is power. Yeah. Second one. So this is nanomaterial. ইলেকট্রিকটা দেখতে হবে মনে হচ্ছে সুইচটা গেছে। Okay, so this is small nanoparticle. When it is in atomic state, that it is colorless. But when it is around 1 nanometer, very interesting, it is become orange color. The gold become orange color, but most interesting part, you can see this is a non-metallic. So gold, we know it carry current, it is carry electricity, but you can see this is non-metallic. So size actually very important. When it is 3 to 30 nanometer, it looks like metallic, means it can carry electricity, and it red in color. So color changes always happen. But what happened between 3 to 1 nanometer? So between 3 to 1 nanometer, that is actually semiconductor. So as you can see, just changing the size of a gold, we can change the color, but most interestingly, we can change its electrical property, its conductive property, lot of things we can change, making this nanomaterial. Okay, so nano is different. So you see over here left side, in the micron scale or larger scale, classical physics determine the properties. In angstrom scale, quantum mechanics determine the properties, but at the nanometer scale, fundamental properties depends on exactly how big the nanomaterial is. So it depends size, shape, and properties of this particular nanomaterial. Now let's see the properties. What are the new properties? Properties, optical properties, electrical properties, magnetic properties, physical properties, chemical properties. So all properties actually will change. We can make it smaller nanoparticle, then it happens like that. Okay, so this is very interesting. Let's see the nanoparticle and small particle, why it is more interesting. As you can see, one elephant and one guinea pig, they are trying to sit on bamboo. An elephant is very difficult, feeling difficulties to sit on it, but where this guinea pig is very easily sit over there, and this one. So that means now when it is small, particle is small, their packing is good, their conductivity, conducting heat, conducting electron, everything or whole, everything will be very easier. দেখুন ওদিকে আছে। Okay, so that is this is the thing. Actually, this nanoparticle actually going to give you a lot of information. You see that catalysis. So as a chemist, we always think about the catalysis. Catalysis, you know that particle size smaller, then catalytic activity will increase. You know palladium charcoal. So palladium charcoal having very small particle is there, and that's why the palladium catalytic activity is increased. But in case of nanomaterial, it is very important that not just size, but it is safe and composition, everything is very important. Not only that, it is very easy to recover all those nanomaterial from the system. So slowly we will discuss this part. And why nanomaterial material is so catalytic, strong catalytic activity? Basically, their coordination number is very less. As you can see over here, when particle is larger and slowly you are going to smaller size, and you can see that coordination number is reduced, and as coordination number is reduced, their reactivity will increase. So material or particle in the surface bulk, that is less more stable, then surface, then edge, then corner. So as you can see over here, you can see 27 atoms are there. The middle atom having this one, if suppose it is octahedral, then you can see that all 6 atoms on the surface center will stabilize that one. But what happened to this corner? It has only 3, but other 3 is not there, so coordination number is less, and that's why it is highly reactive. Now, if we make nanoparticles, so how can we make that one? We can take the help of surfactant. Surfactant, you know that it's a large head group and it has a long chain hydrocarbon. You put in water so that hydrophobic part will be inside and this ionic part will be outside, and it forms a micelle. So we can use the help, we take the help of the micelle to form nanomaterial. Another one is, you can see reverse micelle. Reverse micelle will create a nanospace over there using surfactant, and there we can perform composition nanomaterial to perform that. So you see that how can you fabricate nanomaterials? You can see there are basically, I have taken the example 2 so that you can easily understand. Cooperative self assembly. Suppose you want to make a cadmium sulfide nanoparticle. So you have cadmium carbonate and sodium sulfide, put in water and use small amount of surfactant, not above the CMC. You know, critical micellar constant, don't go above that one. Use small of this one, and then you can see cadmium sulfide and so what do you call nickel carbonate or cadmium carbonate. They are inside, and in the surface, basically that surfactant absorb over here, not allow more number of composed material to enter over there and to make this nanomaterial. So ultimately it will form nanomaterial over there. But another pathway is very interesting. That pathway is basically if you make a creation of nanospace using organic solvent, and in that you add cadmium sulfide and sodium carbonate, and you can see it will create this nanospace inside and it will come over here. So it has the advantage that it will form nanoparticle of a sharp size. Maybe you want to make 5 nanometer size, so it may be 6 and maybe 4. But in case of this cooperative self-assembly, it may be 1 and it may be 10. So the population curve is not so sharp, which is very sharp in creation of nanospace. Let's take one example. You can watch, this is the work done by Krishnanko in my group. And he used SDS as a surfactant, and copper sulfate is this starting material, and it is reduced by ascorbic acid so that it can form copper nano material, and that can be used for different type of catalysis reaction. So he used very small amount of SDS, which is below the CMC, and then copper sulfate and ascorbic acid in water, and you can see that this is the copper sulfate inside, and then SDS center over there, and this is the surfactant outside this sphere over there, and it will decompose and perform the formation of copper nanoparticle. As you can see, copper nanoparticle from the outside. If you remove surfactant, you can find over here. But we can perform different type of reaction. As you can see, this azide, it is a homolytic cleavage. Azide, when treated with this type of copper nanoparticle, it will give you carbonyl azide, it will give you amide. Okay. Hey, 1 minute. Hey, তাড়াতাড়ি এসো। মনে হচ্ছে এই চাবিটা বা এই চাবিটা ওই নিচের ডোরে গিয়ে ওই দিকের দরজাটা খুলে একদম নিচে, না না একদম নিচে না, দোতলায় ওই দিকে লেফটে বাঁ দিকের দরজাটা খুলতে। So okay, so here azide will be decomposed and give you the amide, and amide, sulfonamide can be synthesized very easily. And you have oxazolene. Oxazolene can be reduced to corresponding keto alcohol or proline type of compound you can synthesize out of it. Okay, watch over here. So this is the SDS. When treated with water, we just took the solution and put it on a slide, and then we put in the SEM machine, scanning electron microscope, and we watch over here that surfactant inside that there is a copper metal, and outside surfactant over there, and you can see it is very blurred. So they are basically exposed to all different directions. So this is the nanoparticle with surfactant we observe. But if you remove the surfactant, then it will come like this. This is the TM image of this nanoparticle. It is very small and which can be measured using TM. That population curve you can see, it is around 10 nanometers. So it is around 8 nanometer, but it can start from 2 to 11 nanometers. So like that. So it is cooperative self-assembly. So that's why it is not so sharp. But you can go for PXRD and you can find out this exactly what metal is there. So it indicates this is copper, and you can use dynamic light scattering in the solution and you can get this material. So this is the scheme we already discussed, and this is the way that copper nanomaterial form. But you see the catalysis. You know this azide molecule is very neutral molecule, but in the acidic medium, as ascorbic acid is there, so NH protonation takes place. Now N2 is the leaving group, and this electron from the copper actually transfer, and NN bond is broken, and that will be reduced further to give you corresponding amide. But what is the beauty? You know the palladium charcoal reduction reaction, where halogen can be reduced, nitro group can be reduced, double bond can be reduced, and this bromine, chlorine, iodine can be knocked off, and triple bond can be reduced. But in this reaction, it is very selective. It can only reduce the azide bond to corresponding amide, not the other one. So this is the beauty of the nanoparticles. When you do nanocatalysis, that can be done very specifically in a particular reaction, and selectivity is very high. As you can see that when you have a oxazolene like this and you treat with this copper nanoparticle, that can at 50 degree temperature it will be oxidized, corresponding reduction takes place, and it will give you keto alcohol. But if you increase temperature, it will be around 90 degrees Celsius. It will give you pyrolinone. Pyrolinone compound is a very important compound that can be synthesized. That basically it will open and again recyclize. Let's see the mechanism, how it is working. You can see this is the isoxazolene bond. It is a heteroatomic bond, and this electron transfer to the copper, and this copper actually select this one, copper plus 2 electron transfer, so it will be copper plus 2, and now it will be reduced to alcohol, and now this imine part is slowly hydrolyzed to give you keto alcohol. But when it is heated to little higher temperature, 90 degree temperature, it forms not 6-membered ring but 7-membered ring with the ester functional group over here, and then it's recyclized and it forms pyrolinone like that, and it will give you this product. So this is a beautiful reaction where you can see the nanocatalyst can perform nanocatalysis reaction to give you different type of product. Let's give you the another example. Suppose creation of nanospace. So see this is the one. Just another example I will give you. Throughout my talk, I will take only one example to explain all this observation. So suppose over here you have the manganese, and manganese you can see that KMnO4 and TMSBr is added in dichloromethane. Reaction is very simple. You can study in university simple way, and dichloromethane and manganese will transform to corresponding 7 to 6 oxidation state. So it is very difficult to stop the reaction to 6 oxidation state, but this nanoparticle does this one. And you can see that if you dilute with dichloromethane, then it will edge out. And you can centrifuge this one, as you can see, violet nanoparticle will get. And this is the material in violet in color. But when we go for the DLS, we found 15.4 nanometer size, although we are expecting about 5 nanometer size during our formation of this nanoparticle. Okay, you watch over here. This is the FM. The surface is showing, yes, it's a nanoparticle, but it may be a little bit worm-like nanoparticle, and now small is also there. And also you can see in the UV, there are two peaks. It indicates that two type of nanomaterial is there. This is the mass spectrum. It can show you that what is the MS molecular weight of this molecule, and this is the Ne3SiO2Br. So this is a functionalized nanomaterial basically. And this is the solid state NMR to understand that whether carbon is there or not. So CH3 is there, so that can be done. But we are suffering something that is difficult to understand when we expose to TM being, it is decomposed. The reason is very simple. It is TMS, MN, O2Br and SiMe3. So it is very vulnerable to this heat. And as a result, that when TM imaging is taking place, that you can see it is decomposed. So we took this very small amount and alicot and put on the TEM, what you call copper grit, and put on the TEM. Then we found a very interesting nanoparticle over there. You can see very small nanoparticle, and slowly they grow up. You can see this cartoon. This time over here, you have 5 very small nanomaterial, which is around 5 nanometer size. In fact, that is our expectation. As it is functionalized, they come together from a big nanomaterial around 15 nanometer size, and after that there are 3-4 nanoparticle come together and forms a what you call worm-like structure. You can see this is the worm-like structure, this is a worm-like structure, small nanoparticle coming and aggregated and give you this nanomaterial. And this is also, you can image, this is called energy loss, electron energy loss spectrum, ELS, and where you can excite with different type of atom, whatever present over there, and you can image your nanomaterial. If does not, means it shows black, that means that atom is not there. So it indicates that all atoms are there in this particular material. And I told you that all magnetic property also changes. You can see this is manganese 6, so it is expected 1.1 odd electron, so it is expected 1.7 bm is there, magnetic moment, but we observe it is 2.2 bm. Not only that, it is a hyperfine structure, although manganese 6 should give this type of structure. You can see this is a very hyperfine structure coming out of this. So what we did, we studied squid experiment, and in squid experiment, basically magnetic moment is measured with respect to temperature, and we found very interesting observation. It is pure material. It is not actually mixed by manganese oxide or something like that, as we got more little larger amount of magnetic moment. But it is not there. It is actually a pure manganese 6 nanomaterial. And why it happens like that? Magnetic moment is larger. You can watch over here. All magnetic particle, nanoparticle is a tiny magnet. You can watch over like this, and these nanoparticle actually they are like worm-like structure. So obviously they are vector quantity, and the vector is mostly unidirectional. So that is added, and that's why the magnetic moment is higher. So that's why this metal nanoparticle, even when you are going to synthesize, you have to be very careful that sometimes magnetic moment will not comparable with the expected magnetic moment because of its structure is different. Now we see the catalysis. Very interesting. We have synthesized several types of flavons, azoflavones, thioflavones using this type of compound. And very interestingly, these are very cyclization reaction takes place. As you can see, different catalytic amount, and you watch over here the mechanistic pathway. It is actually this manganese is going 6 oxidation state is coming to 4, and then it is going to again 6 with the oxidation of this is the material is used, that is sodium periodate. So now the question is how it is coming manganese 4. How can you prove this one? Just you can easily prove this one using XPS system. XPS, you can see over here, that is the manganese 6 XPS data. But you can see over here that orange color, this is manganese 6. But there is also another peak, which is a manganese 4 over there. You can see over here, so manganese 6, 4 is also there. And that indicates that nanoparticle is going through manganese 4. Further, it is oxidized by para-iodide, transformed to manganese 6. So this is the beauty of this catalytic reaction we studied. Now let's go for organic nanomaterial. So far we have discussed this, what is nanomaterial, and then we discuss about the inorganic nanomaterial, and we discuss about catalysis in organic synthesis, how can you use that one. Okay, let's see that whether we can make organic nanomaterial. Yes, we can make organic nanomaterial, and you can use this organic nanomaterial for different purposes, like sensor, or it is inkless pen, or you can use like memory device. So slowly we will discuss that one. You know that copper, aluminium, silicon, and silica are the backbone of what you call electronic industries, because silicon is used as a semiconductor, copper is used as a conductor, and silica is used as a insulator. But can we use organic molecule to as a semiconductor? The answer is yes, you can. So you can see over here, organic molecule having very larger size. So that's why you can think that one organic molecule can be one nano building block. So they are making nanomaterial using organic nano building block. You can watch over here. This like a brick, you are making a house. So all this single one is the organic molecule. This organic molecule form this type of nanomaterial, and they have face-to-face interaction, and gluing interaction is used. Suppose in case of when you are making house, you are using cement as a gluing interaction. Here, gluing interaction is van der Waals force of attraction, pi stacking, what you call dipole interaction, ionic interaction, all type of interaction operating over there. And you can watch over here, that is a little bit different, that is head to tail combination over here. And head to tail combination, there is electron flow or hole flow is going through that one very easily. But if you watch like this, one material is synthesized, but one building block is just opposite direction, then it will not give you any electron flow or hole flow. So that's why it is very interesting. And this type of face-to-face interaction when you can make, that is called H aggregate. When you call H to head to tail interaction, that is called G aggregate. How do you know which one is H aggregate? If your material in solution, if you get some UV and you put in the solid state, if you will see that is a hypsochromic shift, means blue shift in the UV region, then you know that is a H aggregate. Means aggregation takes place face to face. Main operating force is pi stacking, and when you will see that it's a bathochromic shift or red shift, that is called J aggregate, and this J aggregate actually give you more interaction, and this intensity also very increased. Okay, so one more thing we need to understand, that whether it can be a P-type or N-type semiconductor, answer is yes. If this material having HOMO, highest occupied molecular orbital, which is larger, then easily it can eject electron and create a hole, and it can be used as a hole carrying nanomaterial or P-type nanomaterial. But when the LUMO having lower, you can eject electron very easily inside that particular material, and that can carry electron, so that can be N-type semiconductor. So organic material having a little bit different concept to make it semiconductor, and as well as making it material. Let's give you one example. Very interesting, this example. And you can watch, this is a solar cell. Solar cell, you have the glass electrode junction, you have silicon, that is N-type silicon in the upper side, and P-type silicon in the bottom side. And sunlight is coming. Sunlight basically it is a photon. Photon is hitting that one and ejecting electron out of that. And that electron actually stored over there, and as a result, hole is created in opposite side. There is a voltage difference out of that. If you put bulb, then you can get light, or you can use battery to recharge it, and you can use every night, and you can get light out of it. Let's see that what happens if silicon, I remove silicon, I put pentacene. Pentacene is nothing but 5 benzene molecules are fused together. So that is called pentacene. And it is observed that 46% of incident light only give you the light or the current, but 54% is waste. It is waste, basically it is absorbed, or it can be reflected, or it can be refracted like that. But what happens when you have pentacene over there, then it is observed that it will give you 43% more sensitive than the theoretical value. That what does it mean? It means if you have 100 photon, in case of silicon, that will give you 46 photon, what you call electron ejected over there. But when you have pentacene over there, 143 photon will be ejected. So almost one photon is ejecting 2 instead of 1 electron like silicon. There 2 electron is ejected. You know that in aromatic system, pi bond, pi clouds are very loosely bonded, and as a result, photon ejecting instead of 1 electron, ejecting 2 electrons. So that is the best use of organic nanomaterial, and as a result, you will see in the future everything is organic electronics. It is called organic electronics, or it is called, when it is material, is nanomaterial, then it is called organic nanoelectronics. So how this organic material is formed, they have different type of interaction. Over there you can watch hydrogen bonding, pipeline stacking. So these are the pipeline stacking over here to make this type of pentacene nanomaterial form over there, and it can be used as a nanomaterial. You can see that usually people say that big molecule can give you nanomaterial or polymer, but we are showing you that very small molecule like imidazole, that molecule you can see broccoli type of the nanomaterial is synthesized. It is like a nanofiber, it is a nanoseed, it is a nano belt type of structure, nanorod type of structure. All these small molecules, they can give you different nanomaterial. Now let's see that what are the driving force. Again, we told you that the driving force are pipeline stacking, hydrogen bonding, ionic interaction, a lot of different type of interaction. You watch over here, you have this compound having an interaction, having methyl hydrogen is making bond, the strong bond with the hydrogen bond over here. You can see over here. So this is a donor acceptor hydrogen bond over here in the methyl hydrogen. Usually we never expect this type of interaction, but in the molecular crystal lattice, it will form this type of interaction. You watch over here that several molecules can come together and they stack each other and give you different type of nanomaterial, this type of nanomaterial form using stacking. And these are the different, you can see red color, green color, blue color, all those are basically weak interaction operating between them and bringing all those molecules together and making this different type of material. You can watch over here, it's a nano belt formed by a sugar molecule, is a chiral molecule, and you can see when it is a J aggregate, as you can see, this is the small molecule when in dilute solution, that is the UV curve, it is giving 260 nanometer. When it is a nanomaterial, it is giving you 490 nanometer bathochromic shift over there. Even fluorescence also 360 nanometer, giving you 425 nanometer. So this is basically J aggregate, and this is the example of nanomaterial. Let's see that how can we use nanomaterial for different type of application. You know, phosgene is a very poisonous gas, and it can kill people. And when you smell this one, and it is not only that, it is colorless, and also it doesn't have any odor. So it's very difficult to sense this one. So can we sense this molecule? You watch over here, this is the receptor we have synthesized. This is the simple method. And this molecule, basically a very good molecule to react with phosgene, COCl2, within a second, within a millisecond, and give this oxazole. formation, and it can be used as a sensor to trap. You can see that phosgene to give you this one. So let's see how can you understand that this type of reaction is going on. You can see over here, this is the HA and this is the HB, this is the oxime OH and this is the phenolic OH is over here. And when you expose the phosgene, and you can see after that NMR taking, that you can see very easily that this bond, these two type peaks are going slowly reduced, and finally will give you this molecule, oxazole molecule, this one. As you can see, that is UV absorbance. You can see this is a green color is coming out of it. And you can see this is the sensing. It is very simple. You take this solution of this material in a strip of the paper and keep in the environment of phosgene. You can see as a result, when small amount is there, that color is different, and when slowly increase this color also increases to strong blue, means very high concentration of phosgene. So this is a very good sensor, and it will not overlap with any other type of compounds. Over here you can see this different type of compound is used, thionyl chloride and other compound, PCl3 and other formaldehyde, but there is no that type of sensing. So it is a very selective sensing compound. But you watch over here, this material, this is the organic nanomaterial, and you can watch over here that is organic nanomaterial when phosgene is not reacting, slowly it is reacting. You can watch over here, this become blood, and slowly when highly exposed with this phosgene, and you can see that completely nanostructure has gone and macro structure will come up. So this is a very interesting part of nanomaterial. So where you can use as a sensor, as this compound, this receptor is used as a sensor to record phosgene. You can see another very interesting compound. This is basically a peptide molecule. Peptide molecule is over here, and it is a dithiophenol type of structure, and it has two halogen. This halogen basically give you the halogen bonding. This paper just published in ACS Material Interface, and you can see over here this halogen form, halogen bonding with oxygen, nitrogen, and halogens like that, and they make a very nice aggregate form. As you can see, this material can be used as a sensor. Sensor means solvent sensor or moisture sensor. You can see different color with different solvent. It can give you different type of gel, so light emitting gel, and it can give you aggregation induced emission. But most interestingly, this compound also sends cyanide in water. So you see this organic molecule modified with peptide, which sends cyanide. You know, again, cyanide is a lethal compound, and people can die if you drink water with cyanide. And that cyanide can be detected very easily. As you can see, that color appear over here. So nanomaterial can be easily transformed to this one and give you this nanomaterial. So as time is less, so I'm not going to discuss elaborately that part. You see the another one. Again, it is a very small molecule. You can see this is a aldehyde, and you have corresponding active CH2 with CN. So you condense this one with a base, so you will get this molecule. It is basically donor and acceptor in the same molecule over there. And this is a very interesting molecule because it can absorb DMSO and give different color according to the content of DMSO. If you heat this molecule, it will remove DMSO, and it can give you red color material like this. But when it has very large amount of DMSO, then it will give you a very green color nanomaterial like this. Okay, how can we use this one? So this is called self-erasing sequencing system. So this is the nanomaterial. You can see this is your organic compound, and this red one, orange one may be DMSO. So DMSO is trapped inside this one. I'll show you that how it is trapped. Basically, they have a very good hydrogen bonding between them, and that's why it is trapped. And when you heat this one, that DMSO will be removed and give you this material which is having no DMSO like that. But how can you use that? When we are very young, we used to use stencil, right? So stencil we use in paper, put the stencil and write ABCD and remove this stencil, then the ABCD is there. So that is our basic understanding when we started our study at our young age. Okay, let's see that how this DMSO is removed and how it looks like. See this nanomaterial is very sharp. When you heat this one, DMSO is removed and it will give you a nanomaterial which is actually not sharp, other than that is blood structure. So basically DMSO is removed. Okay, so DMSO, removal of DMSO can be measured by IR spectroscopy, or you can easily measure by other approaches, by Raman spectra. So you can do it very easily. As you can see, with the heating, it is performing this molecule. As you can see this structure, this is the DMSO having 4 phenyl ring, and this is the DMSO. Basically, they have a hydrogen bonding. This is called dipole-dipole interaction. The pi cloud having aromatic ring, and this oxygen having electron deficient. So it pull electron towards itself, and as a result, DMSO remain between the 2 molecules of that particular nano building block. And when you heat this one, that kinetic energy of this DMSO is high, then it will come out, and obviously there will be no writing skill of that particular material. Let's see that how can you do that. So this is the utensil. This is your small plastic with your compound. There is maybe 5 milligram of compound is sufficient for this one. So paper is ready for writing. You put your slide. Now you use sunlight. Then remove your pencil. You can see that A, B, C, D, E, F, G, H, everything is written over there. Now if you erase this one, you expose to DMSO, again your paper is ready. Now you can rewrite. So very interesting observation. So you can just last one little bit, expose to DMSO, your paper is ready. So you can write, you can rewrite, you can erase. So now this technology is very simple to you. You don't need to use cellulose paper. You don't need to use costly things. So you can use and reuse. Okay. So what's this one? So is it sunlight is essential for this? This concept is completely different. Now you have this stencil paper over here. Not stencil paper. Your paper is ready with this material and having DMSO. Now you have a pen. It is called inkless pen. There is no ink. But what we did, we put a battery so that tip of this pen become warm, and you can write on that particular paper. So you can write just with a pen having inkless pen. Okay, so you heat this paper, and then it will be you can reuse this one. You expose to DMSO. Now paper is again ready to rewrite this one. Now the question is why it is called inkless pen. That is I explained. Now why it is called security material. Security material, it is called, the reason is, suppose there is a fight between two what you call builder. They are claiming they are building, that both of them they are claiming that they made this building, and it goes to court, and they should confirm that who is having that property, like that. So suppose 30 days, so judge told them that okay, after 30 days you come and you prove that this is your building, and then you take your material. So suppose within 30 days they cannot prove that this is not no one having this particular building, then what to do? So that will be program that deed is made like using inkless pen, and it is kept in a chamber, and the chamber is programmed in such a way that after 30 days the temperature will increase inside around 50 to 80 degree temperature, and as a result all this written over there in the deed, that will be clear. So after 30 days when they will open this one, they will find only this paper, there is nothing written on it. So this is the beautiful use. Let's see one device. You know RAM. RAM is random access memory, so it is used with organic compound. RAM is used. So RAM nowadays it is used, but RAM is not that much efficient. So can we make RAM having strongly, you call it usable, means memory strength will be much higher. In that particular case, can we do that? So you can do that. So how can you do it? So suppose this is a molecule, you can watch over here, this is a semiconductor. This organic molecule is a semiconductor. And this semiconductor you can watch over here. So you have a keto amide. So basically it is pulling electron itself. So it is a resistant. So this is called off state. So basically two state is there, that is off state, higher energy. There is a on state, that is lower energy. So you can see if they tautomerize this hydrogen, this amide bond, it can form a double bond with OH. Now you can see this electron can be pushed towards itself, so it can act as a what you call carrier. So this is a resistant, this is a transmitter of electron, so it can carry electron towards itself. Okay, so this is on state, that's why this is called off state. Now, can I stabilize this molecule in the off state? Yes, you can. You can stabilize with the acid molecule, and that will form hydrogen bonding and it will stabilize this one. But small acid like formic acid or acetic acid not allowed because these are volatile. But you can use stearic acid, it's a long chain hydrocarbon which can stabilize and give you hydrophobicity so that it can make an organic nanomaterial, and that can be used in this way. So this is the DFT calculation which studied this way, that this is the material you can synthesize. This is different type of molecule we have synthesized after DFT calculation studied, and you can see this is the molecule is a very good. It's a nanomaterial, it's nanofiber after nanoparticle, spherical nanoparticle in the spin coater if we get it. Okay, so this will give you nanofiber, small nanofiber. But when it is used with stearic acid, so it forms a nano needle like this. Okay, so this is a different type of thing. This is called LV. LV we use and then understand that what type of surface pressure is there. How can you use this one? You can watch this molecule having where is it is voltage. So it is basically IV curve, voltage and current curve. And you can see when it is 0 voltage, you are increasing up to 1 voltage, there is no current. But when you come to around 1.9, slowly huge current is passing through. That basically when you come up to 1.9, there is nothing that remains as amide bond. But when it cannot resist that current, what happens? The tautomerization of hydrogen takes place, and we tautomerize this one and double bond in, and it conducts electricity, and it forms like that. And you can see over here when you have this stearic acid, so even greater than 1 volt, less than 1 volt, that already current started. That means it is a very good conductor of current. Okay, so when we make the device and see initial observation, which is bold, then this is the way which is called actually RAM, or what's called the RAM property. You can write, you can read this type of thing. Okay, so this is the device we made. And you can see this is the glass electrode, and this is the gold, and this is your blue is the organic material, and then again you put this nano gold lining, and now you can see you attach this one, and the device looks like very thin plastic like that, and that is actually a device, and this is called organic crossbar memory device. Okay, so that it looks like when imaging in the same, it looks like this is the material and this is the gold electrode and this is the material like that. Now let's see that what is happening. When stearic acid is more inside of that, and then it is observed that slowly you increase this voltage, it goes to 1.5, suddenly went up, you reduce this one, then it will come up to plus 1.5. But it is expected it should come like this and reach over there to make a RAM, but it does not. It go back in the same pathway like that and reach over there. So that is the beauty, and this is called light once read many. So this is the resistance of LRS. It indicates it is HRS. You can see this is HRS and this is LRS, and it is highly stable, and it is in the 10 to the power 4 order. The memory strength is very high. You see the other one where we use less amount of stearic acid, then it is observed that this is basically nothing but a RAM. And here as you can see that you reduce this voltage, it will come like this, it went up, and increase again it is going to 1.5 and coming this way. That means You can write, you can read. So this is the both way. You can use this one here also. It is for 5 order of stability. So organic material, you can watch de novo polarization conjugation mechanism. So this is the way it pushing electron. So this is the resistance. That's why it is off state, and this is the on state when it is tautomerized. And you can see this is highly tautomerized on state when stabilized. So this is the thing remains more stearic acid, where we found right ones read many type of application, and when you have less type of stearic acid, so that is basically this type of condition. But here this two condition between them when you have a RAM or RRAM over there. So this is the application. It has different type of application. ORM we are calling organic resistive random access memory. But you can see, you can use database, you can use active global memory, electronic voting, radio frequency, all this type of application it is there. That means electronic voting machine. So there is a fight between different politicians that voting can be changed pattern. Yes, it can be changed, but now if you use this material, you cannot change because that magnetic moment is used to change this particular vote current. But as it is organic material, there is no movement, there is no what you call magnetic impulse. So it will be this one. So now I am thankful to my students who are doing PhD and postdoc, and also thankful to my collaborator and also the funding agency, CSR, UGC, CRB, and nanotechnology, nanoscience and nanotechnology, DST. And thank you very much for your kind attention.
Thank you, Professor. Hello. I think I'm audible. Thank you, Professor Maiti, for your very interesting area of research, having a wide range of practical application, and that's a very nice presentation. We have a few questions in the chat box. So one of our students asking, sir, why gold dimension is less than 1 nanometer behaves as non-metal?
Okay, so basically it depends on size dependent phenomena. So small nanoparticle can it is called de Broglie equation. You know the quantization takes place with de Broglie equation. When it is very small, then de Broglie equation number of frequency is very high, and as a result, it gives you different color. But not only that, when it is very small in that particular range, it acts as a resistor, so it cannot flow current through it. It is due to packing of this particular nanometal, and it happens like that.
Okay, sir. So another one more question. If titanium nanoparticle used in paint and clean the air, so her question is, can titanium nanoparticle clean water?
Titanium nanoparticle cannot clean water. The reason is different type of material present in water. Suppose you have the water in the suppose you have the water in industry effluent. Then they are completely different. When you are taking water from the pond, that is different. And when you are taking water that is also different. So that's why you need different type of nanomaterial for that one. So that type of component can be trapped inside them. Okay, so it depends on what type of material present in water. So that type then you need to design different type of material for different type of water. Raj?
Okay, sir. Okay, sir. Yeah. So another question: what is the fate of nanoparticle OH? Are they a matter of concern?
Can you tell me again?
Sure. What is the fate of nanoparticle OH? Are they a matter of concern?
I cannot understand the question.
The fate of the nanoparticle OH. What is the fate of the nanoparticle OH?
What is
Am I
the
state of nanoparticle waste?
nanoparticle waves? What you want to know? I can't understand. Okay, go to the next. Go to the next question.
Yeah. So another is just a minute. Please comment something about the reproducibility of organic nanobiosensor.
Okay. So that is actually different phenomena. Organic nanomaterial you can use this one, and reuse. It depends on what type of device you are using. Suppose in case of our memory device, there you can use and reuse, you extract this molecule and you can use this one. But the only thing is you need very small amount of compound. So you don't need actually to recover that one, because it is in nanoscale. You need few nanogram of the material to get different type of effect. That's why you don't need to recover this organic material. If you have industrial scale, maybe the large amount, then you can extract with the solvent, and then you can reuse.
Okay, sir. So last question, what about the range of mass of organic molecule which can be used as nanoparticles?
Okay, so this is range of mass. It is different because it is different because mass is different. The reason is that small molecule can be nanomaterial, large molecule can be nanomaterial, or maybe large polymer also can be nanomaterial. So it depends on what type of material
It
you
does
are
not
using.
depend on the mass. Yeah,
So
exactly.
that's why you don't need to know that what exactly molecular weight. You need to know what type of weak interaction present in that
The
particular molecule.
non-covalent interaction, exactly, sir. Okay. So yeah, there are no more questions. So with this, I'd like to thank you, sir, for being with us and giving the some time in our webinar with this from your busy schedule. Very thank you, sir.
Thank you.
So in this point, I would like to mention that the technical session 1 is finished. In this session, we have learned many things from Professor Dash and Professor Maiti, who delivered their lecture from the laboratory-based synthesis of molecule and their application in our daily life and also in the different aspects. So I would like to, on behalf of the organizing committee, I would like to conclude this technical session 1, and there will be a 1 hour, not 1 hour, it's 50 minutes lunch break. We'll be back just sharp 3 p.m. with Professor Tapan Pine. Thank you. Thank you, sir, for being with us.
Very good afternoon, sir. Just unmute. Yeah.
Yeah, can you hear me? Hello?
Hello. Am I audible, sir?
Yeah, I can hear you, but can you hear me?
Yes, sure. Yeah.
Okay, fine. Is that clear? Hello, Pujari, how are you?
Yes, sir. So nice to see you.
Yeah, nice to see you again. How are things going?
Yes, Dr. Nonde, will you start the session then?
Okay, so just a minute.
I think
we can start at sharp 3 p.m. We start at 3 p.m.
Okay, I think it's just for 2 minutes to 3. So you are in ISS?
Yes, in office.
Yes. Looks like it.
Yeah. It's the normal for us.
Yes. You have to be regular.
Yeah, we have been coming from June every day.
Yes. After the initial lockdown was lifted.
Right. Since June, we have been coming almost every day.
Yes. But not for us here because our university is slightly in a remote area, semi-urban area. So
Right.
the transport to that place is a problem.
Right, it's very difficult to commute there because
Yes.
Unless you have your own, car or anything.
Yes, absolutely. But we are keeping in touch with students through online classes and things like that.
Yeah.
Only way to keep in touch.
Yeah, that's the only way we have to survive with this.
Yes. Dr. Nondi, I think we can start. It's 3 almost. Yes.
Good afternoon, everybody. Welcome back in our second technical session. We're very happy we have with us Professor Kapur from the Indian Association of Computational Science. So before starting his speech, I would like to transfer the session. I would like to request Dr. Pujari Banerjee to chair this session.
Thank you, Dr. Nandi. Okay, so we begin this technical session, the second of our technical sessions this afternoon, with an introduction of our esteemed speaker, Professor T.K. Pine. So, Professor Pine graduated from the University of Calcutta and went on to IIT Kharagpur for his MSc. He then completed his PhD with distinction from the Max Planck Institute for Bioinorganic Chemistry, Germany, under the supervision of Professor Phalguni Chaudhary. He then went on for his postdoctorate to the University of Minnesota, and he has been a very prominent inorganic chemist since then. Currently, of course, he is a professor in the School of Chemical Sciences, Indian Association for the Cultivation of Science. Sir has many honors and fellowships to his credit. So he was awarded the Max Planck Society Fellowship, the German Research Council Fellowship. He was honored with the INSA Medal for Young Scientist, also the A.V. Ramarao Foundation Young Scientist Award. He is the editorial advisory board member of distinguished journals like Inorganic Chemistry and the Journal of Biological Inorganic Chemistry. And he has been the recipient of the Professor B.N. Ghosh 80th birthday commemoration award from the Indian Chemical Society. He has been the recipient of the bronze medal from the Chemical Research Society of India. And so I'll just tell you briefly his research interests. It revolves around development of functional models of O2 activating non-Hem ion enzymes, dioxygen activation, and bio-inspired oxidations by transition metal complexes, mechanistic studies of oxygen-dependent transformation reactions mediated or catalyzed by biomimetic complexes, application of biomimetic complexes in aerobic degradation of organic pollutants, and development of non-platinum metal complexes with therapeutic potentials. So he has over 80 publications to his merit in various renowned journals. And of course, Sir is also a vastly experienced teacher at both the undergraduate and postgraduate levels. On a personal note, yes, he was also a teacher during our integrated PhD days in ISCS, and I can tell you without bias that Sir was a very good teacher. We learned a lot of inorganic chemistry just by following his classes. And I'm very privileged to be able to introduce you, Sir. And thank you very much for joining us in this webinar. I leave the stage to you now, rather the screen to you now. Thank you.
Okay, thank you, Pujarini. It's really great to see you now as a faculty. I still remember you were probably my second or third batch when I started teaching here at ISCS. And as you know, teaching is one of my passion, and I actually teach a lot, unlike many other colleagues here at ISCS.
Yes, we benefited from that, sir.
Yeah, it's not because I do not know what students learn, but I learn in the process a lot. And in fact, this is precisely, I would like to tell you that many things I learned from students which eventually been translated into my research, and we could do something from there. So today, what I am going to talk is on something that is a part of one of our research area. But as Tormoy told me that there will be a large number of undergraduates and master students who will participate in this webinar, I thought of dividing this particular talk into two parts. So in the first part, I'll focus primarily in a more like a tutorial way to give a background of this research. And then slowly I'll take it to the level of what we learn in the process. And I'll take you through this endeavor of our journey in understanding how Mother Nature utilizes oxygen, or I would say dioxygen, from air, and exactly what is the implication of this kind of reactions that depend on oxygen in industry, and also its usefulness in understanding the biological reaction. So now let me take you to the slide. Okay, so can you see this?
Yes, sir, absolutely. We can see and hear you very clearly.
Oh, okay, very good.
Yes.
So now let me take out one of the pointer. That's fine. Okay, so as you can see from here, the title of today's discussion is the reductive activation of dioxygen by some iron-containing enzymes, and how Mother Nature utilizes this oxygen from air to carry out a myriad of metabolically relevant biochemical reactions. We will try to understand that this is one of our research area. As I mentioned at the beginning, we'll try to understand how Mother Nature does it, not using enzymatic system, but simple synthetic inorganic compounds. So let us take you this reductive activation of dioxygen. What is that? And then how enzymes activate this O2 molecule. And eventually I'll show you what we learn in our studies from synthetic systems what would be the reaction mechanism of those systems. So I'll just start with a simple molecule O2 from air. As all of you know, that oxygen is essential for aerobic life is because of the fact that oxygen is a terminal electron acceptor, and that oxygen is utilized for the oxidation of organic compounds, particularly burning the food that we eat, eventually forming carbon dioxide that we breathe out, water, and a large amount of energy. And this energy is stored in mitochondria in the form of ATP. Whenever this energy is needed, we just utilize that energy, and that energy, chemical energy, is converted to different forms of energy that keeps us alive and doing everything. So this reaction, as you can see here, is a thermodynamically favorable reaction because your delta G for this reaction is in fact a negative, so it's a spontaneous reaction. But one interesting thing all of you have noted that this reaction could be thermodynamically feasible and spontaneous reaction, but this reaction does not take place just like that. The food that we eat is burnt to keep carbon dioxide, water, and energy, but that's within our physiological system. But the same food, when you keep it on the table, this is an organic compound, and you have oxygen everywhere. Moreover, you have organic compounds everywhere, wherever you go, our food, our clothes, whatever we see around us, most of them are made of organic compounds, and oxygen is there everywhere. So if the reaction is thermodynamically favorable reaction, why these two, or these organic compounds and oxygen, coexist? This lack of reactivity of organic compound and oxygen, in spite of the fact that the reaction is thermodynamically feasible, the reaction is not kinetically favorable. And the reason is, you can get it from this interesting electronic structure that we all learn in our PSC first year undergraduate class of molecular orbital of O2. So just if you look at the molecular orbital of oxygen, you have two unpaired electrons in the antibonding molecular orbitals. So if you just look at this, you have two unpaired electron, means your total spin is equal to 1, total spin, so 2 into half. And then multiplicity, the many ways you actually can keep those two electrons are 3 different ways you can keep that electron, what is called multiplicity. So you have an organic compound which does not have any unpaired electron. That's basically your S is equal to 0. So your multiplicity is 1. So the organic molecules are singlet quite often unless they are radical species. And oxygen, therefore, is a triplet molecule. At the end of this reaction of organic molecule and oxygen giving carbon dioxide and water, your carbon dioxide, there is no unpaired electron, therefore that's also a singlet species. Water is also a singlet species, and therefore, as you can see from this reaction, that the spin does not match on the left-hand side and on the right-hand side. So therefore, the spin, this particular electronic configuration and triplet spin ground state is actually responsible for its reactivity because it imposes a kinetic barrier, and therefore organic molecules and oxygen coexist together, and this is precisely called an oxygen paradox. So the question is how we can activate oxygen to make it more reactive, because a triplet oxygen is not reactive due to the kinetic barrier. So there are many different ways by which you can activate oxygen or you can react oxygen. For example, you can just do photochemical reaction using a photosensitizer, and triplet oxygen can be converted to its excited state singlet species, and the singlet triplet energy gap is in the order of about 23 to 25 kilocal per mole, so it's like 95 kilojoule. And that is the process where you can get a relatively unreactive triplet species to a very reactive singlet oxygen molecule. That can be done, and many reactions deal with this triplet to singlet reactions. But enzymes do not take this particular process because you just cannot use a photosensitizer there, or you cannot use a light. You can oxidize oxygen, but as you understand, that removing the electron from the pi antibonding molecular orbital is actually a very difficult task, and therefore this is an uphill reaction, and you need quite a high energy to make it an O2 plus. Our dissociation of oxygen again requires a quite large amount of energy to give two oxygen atoms, and therefore these processes are not feasible in biological system because biological reactions takes place under ambient condition at physiological pH and without use of any other photosensitizer or any other strong oxidizing agent. So Mother Nature precisely rely on the right-hand side scheme. That means you know that if we just go back here, oxygen, you can see you can give electron here, you can inject electron. So after one electron, this will be a superoxide species. You can give two electron, you can give a peroxide species. So superoxide and peroxide, still your electron will be in the anti-bonding orbital, all will be paired off. When you put the third and fourth electron, those two electrons will go to the sigma star. And therefore, eventually when all the electrons will be filled up, then there will be no bonding. So your bond order will be 0. That does mean that OO bond will eventually be cleaved. So by injecting 4 electrons, you can reduce oxygen to water where there is no OO bond. And therefore, the sequential reduction from superoxide to peroxide and eventually to water or oxide or hydroxide, whatever you call it, these are called the reduction process. And in fact, Mother Nature in the process utilized this pathway for taking care of oxygen in the chemistry. As I have already mentioned, that the other processes like ionization or dissociation of oxygen requires very, very harsh condition, strong oxidizing agent or very high temperature to carry out those reactions which are practically not feasible in biological system. But as you can see that if you take a metal complex and if we just consider you have a metal ligand complex and oxygen, it binds with that. Initially, it can form a metal ligand complex and oxygen adduct. And then this metal ligand oxygen adduct can also undergo electron transfer, where electron can go from either metal center or from ligand. Either ligand may go oxidized or metal get oxidized, and in the process, oxygen get reduced to water or hydrogen peroxide or superoxide, whatever it is. So in this two-step process, you can just see this capital K, if this is very high and this small k value is low in terms of kinetics, then you basically have a reversible oxygen binding that takes place like in our blood by hemoglobin, myoglobin, or bloods in some other lower organism like hemocyanin in a lower C organism. But if K is low, that means your reversible binding constant is low, but your rate small k is high, then the second reaction takes place spontaneously, and in the process, oxygen gets activated, and this process of activation is called reductive activation. So Mother Nature, in the process of evolution, picked up different metal centers depending on their abundance, depending on their availability, and also their electronic properties. For example, the nature's dioxygen activation involves primarily transition metal ions, and mainly for higher organisms, it's iron, and for lower organisms, it's copper. And in the process, why transition metal ions? Because transition metal ions have open shell electronic configuration, and it can show variable oxidation state. For example, in iron can have, I mean, if I consider a relatively less oxidation or rather oxidation state which are not unusual oxidation state. The usual oxidation state of iron could be iron 2, iron 3, that we know. But as I progress in today's discussion, I'll show you there could be other oxidation state like iron 4, iron 5. You know that iron 6 exists in nature in the form of ferrate salt, right? So this number of unpaired electron in transition metal ions and their availability at the time of evolution, in fact, are responsible for the activation of oxygen, where the unpaired electrons help in pairing with the unpaired electron of oxygen, and eventually oxygen gets reductively activated. So the reversible oxygen binding, all of you know very well, like in hemoglobin, oxygen can bind in different form with the metal center. Like in hemoglobin, you have iron, and there iron can bind oxygen to form an iron 3 superoxide species. It can also form iron 3 peroxo species, or it can form a dimeric species. So many different binding mode of oxygen as a ligand can take place, and so many different possibilities are there that are involved in reversible binding of oxygen in many different organisms that rely on transition metal compounds for their oxygen transport in the cell. But I am primarily interested of the second step. If small k is high and if it is not a reversible oxidation. So where a lot of oxidation reactions takes place, a sequential, very well synchronized mechanistic pathway by which oxygen is reduced and organic compounds are oxidized. So there could be two different types of oxidations or oxygenation. Oxidations are something where substrate is oxidized without incorporation of oxygen atom from O2. Or there is another set of enzymes which are called oxygenases, where one or two oxygen atoms are incorporated into the product after the reaction. If one oxygen atom is incorporated, the enzymes are called monooxygenases. If two oxygen atoms are incorporated from O2, these enzymes are called dioxygenases. So for example, if I consider an oxidation of alcohol to aldehyde, like alcohol liver dehydrogenase. When people drink alcohol, the next morning that person becomes perfectly fine, but he creates a lot of nuisance if he takes too much of alcohol at the time of drinking. Then that is because the alcohol is not consumed, it's not being converted to aldehyde and subsequently to carboxylic acid. So an enzyme called alcohol liver dehydrogenase, these are oxidases. They do oxidation reactions, but in the process, oxygen atoms are not incorporated into the product. So I'll primarily discuss on these oxidases and oxygenases that nature utilizes to carry out many metabolic reactions, which we in fact depend on for our biochemical processes. So, as I mentioned already, that iron is pretty versatile because of its abundance. During the time of evolution, you have a lot of iron in the seabed, where eventually metal ions were incorporated into the protein, forms metalloproteins. And these metalloproteins, when they catalyze some reactions, are called metalloenzymes. And these iron-containing enzymes, which I am particularly interested in, they carry out versatile reactions. Versatile simple reactions like oxidation or oxygenations, say for example, aliphatic CH bond hydroxylation reactions, like epoxidation of alkene or cis dihydroxylation of alkenes. These enzymes are sometimes involved in redox reactions, and they do electron transfer from one center to another center. They can do reformation reaction like beta-lactam biosynthesis. They also are involved in the degradation of aromatic and aliphatic pollutants through cleavage of carbon-carbon bonds, be it in aromatic compounds and aliphatic compounds. So these metal-containing proteins or metalloproteins are usually they use very exotic way of controlling these dioxygen-dependent reactions, and in the process they do a lot of biological functions. And not only that, they prevent many deleterious side reactions, which are called reactive oxygen species formation, and therefore they control those reactions in order to avoid any damage in the cellular milieu. So, just for representative examples that I would like to show you today are shown here, that how they activate oxygen and what are the reactions that they perform. Some representative examples of these type of enzymes are called non-heme enzymes, which I am interested in. That means where you do not have porphyrin ring as a ligand. Here you have amino acid side chains that bind a metal center, and eventually the reaction takes place in this small tiny place in the protein scaffold, where actual chemistry takes place. But the protein backbone plays an important role in controlling the selectivity and the reactivity as well. Whereas for heme protein, you have a porphyrin ring like cytochrome P450s. You have a porphyrin ring, then you have a metal center where oxygen goes there, and then oxygen is activated, and then it does carry out a myriad of oxidation reactions. Some reactions that are shown here are called like alpha keto acid dependent oxygenases. In these cases, this group of enzymes hydroxylate the aliphatic CH bond to form an alcohol products using oxygen as the terminal oxidant. But as I told you that you need electrons for the reduction of oxygen. So this name indicates that keto acid dependent, where in keto acid, you see this is an alpha keto acid. In enzyme systems, this is basically an alpha keto glutarate. That means alpha keto glutaric acid they use. And in the process, this undergoes oxidative decarboxylation. So carbon dioxide is eliminated. Keto acid is converted to carboxylic acid, where one of the oxygen atom from O2 is incorporated here into the carboxylic acid, and other oxygen atom is incorporated into the hydroxylated product. Another interesting enzyme, which I would primarily focus today, the way we understood it, is called risky dioxygenases. This is, in fact, these enzymes are found in soil bacteria. And you know that soil bacteria, we call them always our friends, because this bacteria utilizes many organic compounds to convert evaluated compounds for their source of energy and carbon in soil. But interestingly, these risky dioxygenases, what they do, they convert the first step of the degradation of aromatic compounds like pollutants. These polyaromatic compounds, which are pollutants, they are converted to the dihydroxylated product. So oxygen atoms are incorporated into the aromatic backbone. And once you have the dihydroxylated product, now another set of enzymes come into picture, and then they cleave this CC bond, and eventually at the end, the aromatic compounds are converted to useful aliphatic compounds. So toxic products that we are in fact giving to soil because of our lifestyle, because of many other sources, soil bacteria utilizes those for converting them to useful chemicals. But you just look at this reaction. An aromatic rings double bond is converted to a diol product. So it is more like converting alkene to cis diol product just using oxygen from air. If we just go back to our organic textbooks, what are the reagents that are known? They are all toxic reagents, stoichiometric osmium tetroxide or related compounds are used for doing the cis dihydroxylation reaction. But you see, over the billions of years of evolution, Mother Nature came up with an exciting, a very fantastic way of dealing this conversion by using oxygen from air at room temperature, and in the process, you need 2 electrons. These 2 electrons are provided by an electron transfer protein called risky center that I'll discuss you a little later. And cytochrome P450, the heme enzymes, they convert like non-heme enzymes. The CH bond is hydroxylated, and also the alkenes are epoxidized in the process of oxidative transformation reactions. But how? What is the active oxidant? So if you just look at here, one oxygen atom is incorporated into the product. One oxygen atom is incorporated into the oxidized form of the reductant, that is cofactor, organic cofactor. This means that at some point during the reaction, OO bond got cleaved. Otherwise, why one oxygen is ending up here, another oxygen is ending up here? Whereas here, the mechanism could be different. Similarly, for cytochrome P450, one oxygen atom is incorporated here into the products, and the other oxygen atom lands up as one molecule. So There is, in fact, a lot of biochemical studies, synthetic systems, theoretical calculations. Many people have been working to understand how these enzymes activate oxygen and utilize for oxidative transformation reaction where oxygen is used as a terminal oxidant. It is not the active oxidant. O2 is not doing this chemistry. Someone else is doing this chemistry. And depending on enzymes, the nature of active oxidants vary. So here, if we just look at the dioxygen activation paradigm, where in most of these enzymes, iron remains in the reduced state in class 2 oxidation state. So initially, one electron transfer takes place from iron center to the antibonding molecular orbital of oxygen, forming an iron 3 superoxo species. And this is the starting point where this actually diverges into different pathway depending on the enzymatic reactions, depending on cofactor, and depending on the purpose for which Mother Nature has created that enzyme. So the one electron reduced form is superoxide. So here you have an iron 3 superoxide. Now, if you inject another electron, either from an electron transfer protein or from an organic cofactor which can also provide electron, this can undergo 2 electron reduction. So now you have an hydroperoxo species or alkyl peroxo species, depending on whether you have an electron transfer protein or you have a cofactor. You can have 2 electrons at the same time, then it can form iron 2 hydroperoxo species also. This particular OO bond then can undergo heterolysis or homolysis. So what happens when you have an OO bond heterolysis? OH or OR minus goes out, and what is left is basically 2 electrons are provided by iron center. Iron center is converted to iron 5 species, and in the process, this iron 5 oxo intermediates are generated. In this case, iron 4 oxo species is generated when this is formed upon heterolysis of the OO bond of iron 2 hydroperoxo species. When there is no source of electron source, that means no electron transfer protein, no cofactor, another metal center provides the second electron to the iron 3 superoxide species, generating a peroxo-based diiron 3 compound, which eventually cleaves the OO bond homolytically, generating this high-valent iron oxo species. And most of the cases, this high-valent iron oxo species have been implicated as active oxidants. And interestingly, these intermediates are generated in the protein scaffold to carry out synthetically important, biologically relevant, and very difficult oxidative transformation reaction under ambient conditions, but in a very regulated way. Because eventually, Mother Nature does not like, or biological systems do not like any unwanted side products. So the reactions have to be very selective, chemo, regio, and stereoselective. But what is the control of this selectivity? As I mentioned, protein structure plays an important role in tuning the selectivity, be it regioselective, stereoselective, or chemoselective. But how do we know that how these selectivities are controlled and what are the active species? So as I mentioned, I told you these particular enzymes where it has been shown already. This is the only high-valent iron oxo species that has been tracked in enzymatic reactions and spectroscopically characterized. And this is a high-spin iron 4 oxo species, which in fact oxidizes RH to ROH, and therefore this oxygen atom is incorporated into this CH bond, resulting in the formation of the hydroxylated product. In case of risky dioxygenases, no such high-valent iron oxo species has been observed yet. In fact, the last intermediate that had been structurally characterized back in 2003 is a site-on bound iron 3 hydroperoxo or peroxo species. So is it more like a peroxo species which is doing the cystohydroxylation reaction? Or the OO bond also undergoes cleavage prior to the cystohydroxylation reaction. So this part remains a matter of debate, and therefore we just wanted to know from synthetic systems how exactly the C-hydroxylation reactions take place. So we wanted to ask this question, so what is the basis of this control in enzymatic systems, and how these structurally diverse proteins, they activate oxygen reductively and perform a different reaction with very fast rate and very high selectivity. There are two ways to study that. Enzymologists and biologists, they do enzymatic studies. I am not a biologist. And moreover, there are a lot of problems in studying with enzymes because you need a huge amount of enzyme. Number one. Number two, quite often these intermediates are not stable. Number three, they are quite expensive. And number four, working with enzymes in large scale is not an easy job. And moreover, you need training, which I don't have. And therefore, I am an inorganic chemist. I can make molecules. I can do synthesis. Not I should not say this, my students, because they are the strength. So they can make molecules, and using those synthetic inorganic compounds, we can do model reactions, and then we can try to understand the enzymatic reactions. So what is our model? Our model is that we don't work with enzymes, but we get information from enzymes, either the structure of the enzymes or spectroscopic data of the enzymes we look into, and we try to find out what is the structure and geometry of the enzyme in its active site where metal binds to the iron center. And then we try to develop ligands, the way the metal center is coordinated by amino acid side chain. Say, for example, here in this case, you see that in the iron center, which is 6 coordinate in its resting state, that means when it does not do any reaction, it takes rest. So if you have a 6 coordinate iron center, these 3 ligand from amino acid side chains to histidine and 1 aspartate or glutamate, they bind to the iron center from one face of the octahedron, and the another face of the octahedral iron center is occupied by labile water molecules, where substrate can come in and do oxidation reactions. So if we can develop a facial ligand backbone, we in fact can develop a synthetic system, and then we can have a labile ligand here where substrate can bind, oxygen can be activated, and can carry out these reactions. So these are called synthetic models. We really do not bother much about the protein backbone because it's very difficult to emulate everything in synthetic systems, but stepwise that can be done, which we are trying to understand, and we are also involved in projects that deal with the secondary interactions as well. So then we develop synthetic compounds, what are called synthetic models. These models could be 2 different types. They could be structural models, that means they will just mimic the structure of the enzymatic systems, the coordination environment, the spectroscopic environment, the spectroscopic properties of the enzymes, and the coordination geometry, coordination number, and all these things. But they are not very, very exciting. Particularly, I'm interested not in that part. We are interested primarily on the functional part. That can my synthetic system do the same chemistry what enzymes do? Is it that not that easy? But it requires a lot of planning and designing a strategy. So in that designing strategy, we make ligand, we make metal complexes, then we try to do the reaction, try to find out if the synthetic systems do the similar chemistry. If it does stoichiometric chemistry, we try to do fine tuning on the ligand. That means we do tuning the electronic and structural properties of the ligands. And then we try to find out if the system is catalytic. If not, we try to understand the mechanism by which this synthetic system is doing the transformation reaction. And then we again, based on those mechanistic information, we go back again to the synthetic systems, try to develop a better synthetic system, and this process continues unless we get a catalytically active synthetic compounds which can act as a catalyst which perform the chemistry very similar to enzymatic system. But today, I will not tell you all these catalytic reactions and all. I'll show you a simple chemistry that we have developed over the last 10 years, understanding stepwise the reaction, the mechanism of the reaction, and then eventually where we stand, and that understanding help us in developing truly bio-inspired catalytic system. But our inspiration is this beautiful but very complicated enzymes that perform cystohydroxylation reactions of aliphatic and aromatic substrates. So as I said that during the reaction, oxygen needs 2 electrons, and those 2 electrons are provided by NADH, and that electron is transferred via an iron sulfur cluster, which is an electron transfer protein of iron sulfur cluster, and it is transferred via this aspartate bridge to the iron center of the enzyme where actual chemistry takes place. And in the process, as I shared already, that an iron-3 hydroperoxo intermediate has been observed, and that is the last intermediate that has been observed so far in the enzymatic system. But how this chemistry takes place? Does iron-3 hydroperoxide perform the cystohydroxylation of alkene, or it cleaves the OO bond, forms iron-5 oxohydroxo species, because if this bond cleaved heterolytically, so 2 electrons are pushed to this oxygen, you form iron-5 oxo, then this O bond get cleaved and you form an iron-5 oxohydroxo. 2 oxo oxygen atoms, 1 oxo and 1 hydroxide, they are positioned cis to each other, more like an osmium tetroxide like things. Substrate alkene docks in, and then oxygen atom transfer takes place from one phase of the alkene, and you form diiolate product, which eventually by electron transfer from risky center, iron-3 center reduced to iron-2, and the system gets back into the catalytic cycle. But in synthetic compound, how we can really engineer this beautiful system where Mother Nature required billions of years. So it's very, very difficult. We can definitely synthesize a structural analog of this part. But what about this analog and this thing combined together that would allow you selective electron transfer from a reduced center to the metal center, where oxygen can be reductively activated on this iron-2 center, leading to an intermediate which would perform the cystohydroxylation reaction. So when we started this project, our strategy is that we need sacrificial reductants, that means which will provide electron, as co-ligand. That means we will prepare a ternary compound of L prime type of ternary compound, where L prime is a sacrificial reductant which will provide electron for the reduction of oxygen on the metal center, and in the process iron oxygen oxidant may be generated, which can be utilized for doing substrate oxidation. And this, in fact, idea came from another enzyme I told you, the alpha keto acid dependent oxygenases, where this alpha keto acid cofactor binds to the metal center, which we call enzyme cofactor complex, is formed before oxygen activation takes place. So if I have a reductant which have binding determinant to coordinate to a metal center, then selective electron transfer can take place. I just cannot take a metal ligand complex and I will add L prime separately, then there could be an uncontrolled electron transfer. And in this uncontrolled electron transfer, the active oxidant might get quenched, and therefore the selective electron transfer will not take place. The oxidation by synthetic compounds will not be selective. So therefore, with that strategy, we have explored many different ligands, many different sacrificial reductants, but today I will only share with you a story that was that is based on this supporting ligand, which is called trispirazolyl borate ligand, which is a tridentate facial ligand that emulates the facial binding motif on many non-heme iron enzymes. Iron-2 center and different sacrificial reductant like alpha hydroxy acid. We all know that alpha hydroxy acid can undergo 2 electron oxidation, and in the process carbon dioxide is eliminated, and this form carbonyl compound This one comes out as carbon dioxide, and in the process, 2 electrons are ejected, and those 2 electrons can be utilized for the reduction of oxygen on the iron center. So using that thing in mind, back in 2011, we synthesized this compound, a ternary iron 2 mandolate compound, an alpha hydroxy acid. You have a 1 phenyl group and 1 hydrogen at the carbon. You have a hydroxyl group here and a carboxylate group here. So facial tridentate ligand binds to the iron center, and the alpha hydroxy acid anion binds to the iron center as well. And here you have a water molecule coordinates to the iron center. This is pretty labile, so oxygen activation can take place here, as is very clear from its reaction with oxygen. It instantaneously, within few minutes, this is a high spin iron 2 compound. As you can see here, the colorless optical spectral feature. There is no feature, so it's a colorless compound. It's a high spin iron 2 compound. But immediately within few minutes, the colorless compound turns green, and the green species is an iron 3 compound. A rhombic signal in the EPR spectrum at G equal to 4.3 indicates that you have an iron 3 compound. So at that point, we thought, what is the point of making this compound? I start from iron 2, I can open it to air, it turns to iron 3. What is fun? Nothing. You can take any iron 2 compound, expose it to, or you get iron 3. But then what we found out that we analyzed this green solution by ESI mass spectrometry, and what we found an iron peak at 740. This 740 peak corresponds to with the isotope distribution pattern. So this isotope distribution pattern matches with the iron compound of a ligand where we started from, along with an oxygen atom inserted in it minus hydrogen. That means one of the ligand phenyl groups on the ligand backbone is hydroxylated during the reaction. Why is this? What happens? So iron 3, you have a phenolate unit, it binds with the iron 3 phenolate, and this green chromophore at 600 nanometer is nothing, but it's a phenolate to iron 3 charge transition. But my student who started this work, he was my second PhD student, Shayanton, when he thought that, okay, let us see what is happening. And he ran this mass spectrum several times. And what he found, that in addition to this iron peak, there is a small iron peak is there at around 884. The isotope distribution is not very well defined, but it says that you have an 884. And this is nothing, but it is again a hydroxylated ligand, iron compound with a benzoate. But you have an anionic ligand, so 1 and negative charge from the ligand itself. The phenolate, you have a second, so TP phenyl star is a dianionic ligand, benzoate is an anion, so trianionic, so 3 anionic charge. Iron is in +3 state, so it is neutral. It does not fly in the ESI mass spectrum, and therefore a sodium atomically flies, and it shows up here at 884. Interesting. Where this benzoate come from? Is it coming from mandolate? Then how? Then we analyzed the organic products derived from mandolate, and what we found very interesting. The NMR spectrum, GC mass spectrum, all different analysis suggest a very funny combination of different products. I have 70% benzaldehyde, which is a major product, expected, because if you start from mandolate acid, it will oxidize by 2 electrons to form benzaldehyde plus carbon dioxide. But I have 20% benzoic acid, about 10% benzyl alcohol. So it was pretty complicated at that point. We thought of, okay, we will understand that thing, but let us make life a little less complicated at the beginning. So Shayanton came up with a very interesting idea that why deal with this? But I told him, okay, what you do, Shayanton, you just run a leveling experiment to see what is the fate of oxygen and eventually where this oxygen atom of O2 are eventually landed up. So he ran that. Instead of normal oxygen, 18 isotope level oxygen he used, and he found that the 740 peak with the normal oxygen now shifted to 742. That means the oxygen of the hydroxylated ligand, the phenolate unit, also derived from O2. In addition, this peak at 844 now shift to 888. So 4 mass unit shift. So if you have a 4 mass unit shift, indicates that there are 2 oxygen atoms are there, and that 2 oxygen atoms can be 1 oxygen atom into benzoate and 1 oxygen atom from the phenol group, which is originated from O2 in the phenolate product. That explains partially the chemistry. And then he tried also to understand what exactly happens and in the organic compounds. So what he found that in benzyl alcohol, which shows up ion peak at 108, now she shows both ion peak at 108 as well as 110 when the reaction is carried out with 18 isotope level oxygen. And from all these leveling studies, what he concluded that one of the oxygen atoms of benzoate contains 1 level oxygen, as we have seen from the 884, which shifted to 888. A small percentage of level oxygen is incorporated into benzyl alcohol, very less, and benzaldehyde does not contain any level oxygen atom. So this was our observation until that point. Then I told Sayantan, let us understand that why we'll use mandelic acid is basically because you have this hydrogen atom. Let us remove this hydrogen atom and you put a phenyl group there. So he came up with the compound, which is a benzylate compound here, a very similar binding motif. Instead of an eta-1 binding motif on mandolate, here benzylate carboxylate binds in an eta-2 binding mode. Hydroxyl groups still remain non-coordinated, and you still have an OH group there, and this is 5-coordinate. So this is still coordinatively unsaturated, reacts with oxygen, and shows a similar feature at 740. Upon 18 isotope leveling experiment, this 740 band shifts to 742, and in the process what we got, the organic compound derived from benzylate unit is 100% benzophenol. So the alpha hydroxy acid in the reaction with oxygen coordinated to the ion center, undergoing decarboxylation to form the corresponding carbonyl compound. So in case of mandolate, benzaldehyde was forming, and in this case, benzylate to benzophenol is forming. And then in the mandolate case, benzaldehyde was eventually going to benzoic acid formation and benzyl alcohol formation, the mechanism of which we'll discuss shortly. Then we studied some experiment with radical, a radical quencher like tempo H, which inhibits the decarboxylation reaction of benzylate. And it's the fact that if I use tempo H, and if we consider that initially ion center oxygen binding takes place and a superoxide is formed, this superoxide, it can abstract the hydrogen, weak hydrogen atom from the OH bond, and there can be a competition if I use tempo H in excess compared to the OH abstraction from mandolate or benzylate. So we wanted to know, is the OH abstraction by a putative iron-free superoxo species formed initially from where the reaction diverges? Does it abstract the hydrogen atom from OH group of mandolate or benzylate or any alpha hydroxy acid to initiate the reaction? Then we wanted to see what is the importance of the OH group of hydroxy acid. And we synthesized a series of iron 2 compound with the methoxy derivative of those alpha hydroxy acid. They are not alpha hydroxy acid, they are methoxy carboxylic acid. And synthesized the corresponding iron 2 compound. Here is the crystal structure of one of them. A methoxy oxygen, ethyl oxygen binds to the iron center. You have a carboxylate oxygen also binds to the iron center. Still 5-coordinate geometry, but none of these methoxy carboxylate complexes react with oxygen. They are rock. Even if they are iron 2 compound, you can keep it under oxygen environment for days and nothing happens. So this particular experiment suggests that the presence of OH group on the hydroxy acid is essential for the reductive activation of dioxygen and from the iron-3 superoxo species to a subsequent generation of oxidant, which is actual oxidant intertransformation reaction. But what is the oxidant? Pujarini, how much time do I have?
Sir, I think you can continue for another 5 to 7 minutes. At least.
Okay, fine. So you just alert me because this part I will finish and then I'll just stop. Okay?
Yeah, of course, of course.
Fine. So then we wanted to know what is the active species which is doing this ligand hydroxylation chemistry. A smart move that we had to take because we do not see the formation of any intermediate in the reaction. So therefore, in the steady state, we cannot trap the intermediate. So we had to do indirect experiment. What is that indirect experiment? As I said, that this phenolate to iron 3 charge transfer transition takes place here at around 600 nanometer in the visible region. Now, if I add substrate from outside in excess amount, there would be now an intramolecular ligand hydroxylation by the active oxidant species which is generated and doing the hydroxylation of the aromatic ring. In the presence of excess substrate, there will be a competition between intramolecular ligand hydroxylation and intermolecular substrate oxidation. So we used a range of substrate and we wanted to see how much this charge transfer chromophore is inhibited. And here you see, we used a sulfide like thioanisole. In the absence of thioanisole, we get almost 90% ligand hydroxylated product. But as soon as I add one equivalent of thioanisole, the ligand hydroxylation, that means intra-ligand hydroxylation or intramolecular reaction is inhibited appreciably. And in the presence of 10 equivalent of thioanisole, the ligand hydroxylation gets almost completely inhibited. So in the process, then thioanisole must be getting oxidized. What happens to thioanisole? Thioanisole is converting to a mixture of thioanisole oxide and sulfone. The labeling experiment suggests that 140 peak shift is 142 and 156 peak for the sulfone is now converted to 160. So 2 mass unit change and 4 mass unit change, a monooxygenation reaction and dioxygenation reaction. Then we performed this reaction with many different para-substituted thioanisole and other substrate. But interesting observation is that the ratio of sulfoxide versus sulfone formation that depends on amount of added sulfide. If the sulfide amount is very high, then sulfoxide is formed as the major product. But if I have a small amount of substrate, then the first product is sulfoxide, and that sulfoxide is further oxidized to sulfone. This happens only when an oxidant of nucleophilic nature present in the system and performs the oxidation reaction. Therefore, we wanted to see that what exactly happens with different para-substituted thioanisole. So we did Hammett analysis from the indirect rate of the product because reaction rate we do not have, we do not see the intermediate, but what we know that the reaction rate is directly proportional to the concentration of the product. So if you use thioanisole and a mixture of thioanisole and para-substituted thioanisole, you get the product, analysis of the product, quantification of the product, and then the direct rate, which is an indirect relative rate you can plot with the sigma rho value, and what you get is basically a linear plot from electron withdrawing to electron donating groups, and that shows a positive Hammett slope here in this case. That means the oxidant which is responsible for thioanisole oxidation has nucleophilic character. Then the exciting development came when Sainton one day came by doing the reaction with alkenes. He also found that in the presence of alkenes, the substrates get, the intraligand hydroxylation gets inhibited. And he found that cyclohexane gives you cis-diol product. 1-octene, cis, cyclooctene, styrene all give their corresponding cis-diol product. An example shown here that cyclohexane give you cyclohexane 1,2-diol product, which shows an ion peak at 116. When the same reaction is carried out with isotope leveled oxygen, the 116 peak is now shifted to 120 here. A small peak, but if you zoom it, you will see that this is indeed an ion peak. These are the fragment pattern. So the fragmentation pattern and the ion peak suggest that both the oxygen atom of cis diol are originated from molecular oxygen. So indeed, just like enzymatic reaction, we can use a real oxygen by using a simple iron 2 alpha hydroxy acid compound and can do cis dihydroxylation reaction, but in a stoichiometric scale, because in these systems you basically form the ligand hydroxylated product. So this was the first development that came in this thing back in 2011. So what is the active oxidant? The active oxidant could be a nucleophilic oxidant, because hydroxy acid is undergoing 2-electron oxidation. So these 2 electrons are now used by oxygen for their reduction to form peroxide, which remains coordinated on the iron center. So this is pretty electron rich steel, because iron is a low oxidation state. You have a large number of electrons there. So you have a high electron density on this compound. This is expected to be nucleophilic, as we observed from the Hermet analysis. But it can also be that O bond gets cleaved, and then it can form this iron 4 oxohydroxo species, the nature of which is not known. But it could also be nucleophilic, who knows? But importantly, what we found that if this is involved as the active oxidant for the cis dihydroxylation reaction, the oxygen atom here must exchange its oxygen atom with water. But in the leveling experiment, when we performed the leveling experiment with normal oxygen and isotope leveled water, no incorporation of leveled water into the diol product was observed, which suggests that no, the OO bond does not cleave prior to the cis dihydroxylation reaction. Now I come back, and then after this part is done, I will finish. Now what we observed initially, we found that benzyl alcohol was forming. In leveling experiment, this was a partial incorporation of leveled oxygen of benzyl alcohol from mandolate. So we wanted to see here that let us now have an active oxidant that is generated here, which we putatively assign as an iron 2 hydroperoxide. Now if I add benzaldehyde to the reaction mixture, what happens? And here, interestingly, we get a mixture of benzyl alcohol and benzoic acid. Benzyl alcohol contains partially leveled oxygen. Similarly, benzoic acid, 122 peak, now shows up at 124, that the oxygen atom is coming from O2. Now, we wanted to see how this is happening. So what we did, we took up again this mandolate system, and then instead of mandolate H, so we did substitute this one with a deuterated mandelic acid. And after doing the reaction, what happens, you see that the aldehyde peak for benzaldehyde, the CH, then it should be CD, because if mandelic acid to benzaldehyde is formed initially, you won't see the deuterium peak, the aldehyde peak here at this position, almost absent. And here you see that these two are D, the intensity is dramatically reduced, because one of the hydrogen of benzyl alcohol, if it forms by this pathway from mandelic acid to benzaldehyde and then benzaldehyde to benzoic acid and benzyl alcohol, if this is the case, this intensity is diminished dramatically. Moreover, here, the 2 deuterated benzyl alcohol gives you a peak at 110, and this one is giving you at 108. So how this is happening? This can only happen. Very famous reaction we all know. This is nothing but, the second step is nothing but a Cannizzaro reaction. And this requires an hydroxide ion in the reaction. So how this is happening? We came up with a mechanistic hypothesis for that this particular iron 2 hydroperoxo species is formed initially, and this iron 2 hydroperoxo reacts with aldehyde to form this benzoic acid and a metal coordinated hydroxide. A metal coordinated hydroxide is a very strong base compared to free hydroxide because of the Lewis acidic nature. And this one then attacks this aldehyde group. So now you can have a benzoic acid and you have now this geminal diol. Now, this geminal diol can exist, in this form, that if you have a geminal diol, this aldehydic oxygen can contain a partially leveled oxygen by elimination of a partially leveled hydroxide by this platform. So already prior to the hydride transfer mechanism of Cannizzaro reaction, your aldehyde already contains partially leveled oxygen. So in that partially leveled oxygen, if this hydride transfer takes place, you get benzyl alcohol where you have a partially leveled oxygen atom incorporated, and you have a benzoic acid where you have a partially leveled oxygen atom. And that explains the isotope leveling experiment result. And based on that, we came up with this hypothesis that precisely a mandolate decarboxylation is giving you an benzaldehyde, which is a major product, 70%. And then out of that, the rest, 30% of benzaldehyde is now undergoing a Cannizzaro type reaction. In the first stage, you basically have a benzoic acid formation that takes care of the 10%, and the rest 10% which is left is giving you benzyl alcohol plus another 10% of benzoic acid, affording 20% benzoic acid and 10% benzyl alcohol. So all this chemistry clearly indicates that the active oxidant generated upon oxidative decarboxylation of mandolate or benzylate is an iron 2 hydroperoxo species, which eventually we established for the first time. So this is a nucleophilic oxidant, and I'll just quickly go through the final reaction mechanism of this, that iron 2 mandolate compound first, or benzylate compound first reacts with oxygen to give you iron 3 superoxo species. This superoxo species then either abstracts the hydrogen atom from the OH group, or there could be a proton coupled electron transfer, but OH group is essential. I have shown you by changing this group to OR group, and then it undergoes decarboxylation concomitant with the formation of benzophenone or benzaldehyde in case of mandelic acid. Then it forms an iron 2 hydroperoxo species. This iron 2 hydroperoxo species can perform cis-dihydroxylation reaction, but this does not exchange its oxygen atom with water, and therefore both the oxygen atoms are coming from O2 molecules without any exchange with water. But what I could not share with you, that if we use Lewis acid, like in protein backbone, the secondary residues can also play acid-base chemistry. This OO bond can be cleaved by using Lewis acid in our synthetic systems, and we in fact can cleave this bond, and then we get an electrophilic oxidant instead of a nucleophilic oxidant. That nucleophilic oxidant still does perform cis-dihydroxylation reaction, but in this case, the active oxidant can exchange its oxygen atom with water, and therefore you see the partial exchange takes place. But what this nucleophilic oxidant cannot do is the aliphatic CH bond hydroxylation, but the nucleophilic oxidant perform aliphatic CH bond hydroxylation as well. In the absence of any substrate, this active oxidant, either this or this, chews out itself. So it's like a suicidal oxidation. The phenyl group CH bond is close by, so it hydroxylates the aromatic ring, resulting in the formation of iron 2 hydroxide species, which in the presence of excess oxygen forms an iron 3 phenolate species, which is responsible for the green color of the solution. So this chemistry tells us that a simple synthetic system, if it is designed in a strategic manner and with a proper design strategy, we can develop synthetic systems with which we can pursue and fine-tune eventually to get a system which will show enzymatic like activity after a lot of trial and understanding other parameters involved in dictating the selectivity and reactivity of this kind of synthetic system. So the chemistry that I wanted to share with you is there. It was very easy for me to present this in front of you, but as you understand, it involves a lot of mechanistic studies, a lot of really very hard work. These compounds are not easy to isolate; they're very air sensitive. So you need to spend a lot of time, and I'm always I think, blessed to have really great students who worked with me and helped us understanding these systems. So this work that I presented to you initially was started by Shayantan, who is now an assistant professor at IIT Delhi. And this work was later picked up by Shayanti. Part of what was also done by Vishnu. And later on, this same project was taken up by Shravanti, who all of them graduated. Now, last part, which I could not share with you, Sridhar, who just submitted not just a few months ago because of lockdown, defended his PhD thesis. In February, he submitted his PhD thesis, waiting for his PhD defense, who did quite exciting work in this area, where these intermediates that we proposed initially, he was the first person to track that intermediate and to show that what we proposed 10 years back could be isolated reality, and he isolated the intermediate at low temperature, tracked it, spectroscopically characterized, and confirmed our hypothesis. And the other people in the group created a great ambience because of which we could do this such kind of work and still continuing this endeavor. I must thank my collaborator, Dr. Gaurav Ganguly, former PhD student of Professor Angkon Pal, who is my collaborator for theoretical calculations. A lot of money requires for this research that came from ACRT, Department of Science and Technology, Government of India, Indian National Science Academy as a young scientist project, Council of Scientific Industrial Research, and I have a foreign grant, which is a Swedish Research Council grant that allowed me to do research of my own wish, and I can utilize that money the way I want. So that helped me a lot of liberty to utilize this grant. So I thank all of them, and finally I thank you for your patience and your attention, and I'll be very happy to take up questions and comments and for any clarification regarding the basics of this chemistry or the research results. So thank you very much.
Thank you, Professor Pine, for such an informative lecture, and for starting with something as basic as the molecular orbital diagram of oxygen. So that really takes us back to the basics, and it's what research is all about. So I think we have time for a few questions, sir. So I'll
Sure. I have a lot of time, no problem. Any number of questions I can take up.
Of course, sir. So I have one question from Dr. Nondi. So he's asking about that last complex, I think, the mandelic acid related complex that you were discussing. So does that complex, is it able to oxygen to N oxide? Like, for example, from pyridine to N oxide pyridine?
Okay, so let me tell you, the period. So these compounds like mandalate, benzylate, and the mandalate part was actually very, very useful, as I have shown you, to understand the mechanism of the reaction. But we prefer the benzylate complex because the mandalate complex was happening. Initially, benzaldehyde was forming, and the active oxidant that formed upon the decarboxylation was actually was acting on benzaldehyde itself, giving you benzoic acid and benzyl alcohol, all these things. So therefore, we thought, let us now work on benzylate, where benzylate you get benzophenone, and your intermediate, which is iron 2 hydroperoxide that is forming there, is not acting on benzophenone. Therefore, so it is available for doing substrate oxidation. Now the question is, all these oxidants, this hydroperoxide or iron 4 oxohydroxy species, they perform versatile reactions. They not only can do cis dihydroxylation reaction, but they do but nucleophilic oxidant cannot do aliphatic CH bond hydroxylation. The electrophilic oxidant, if I can generate from the nucleophilic oxidant by adding a Lewis acid, which will pull the electron density from the metal center, and this nucleophilic oxidant is capable of doing oxidation reactions on electron-rich system like aliphatic substrates, like amine, like thiols, like sulfides, and all. So the answer is, having said that, the answer is yes, but for that I need to add an additive, which is a Lewis acid that would generate an electrophilic oxidant for doing oxidation of amine to nitric oxide.
Okay. Thank you, sir. So we have another question that is the functional property of these models going to be iron is replaced by manganese or cobalt?
That's an interesting question. That's an interesting question.
This is a question from Dr. Shanchari Dasgupta.
Okay. So yeah, so this is an interesting point, but as you see, when Mother Nature picked up a metal center for doing the oxidative transformation reaction, there is a reason for it. So the reason is very simple: the electronic properties, the redox properties, stereoelectronic properties, and obviously the protein folding. All these things are important. So we opted iron because Mother Nature uses, or these enzymes uses iron for that purpose. Now, what I could not share with you, if I can share again, let me show you. I don't know whether I have that. I don't have here. But anyway, to answer the question, in case of cobalt, what happens, because the kinetic inertness of cobalt complexes, because it's something to do with kinetic lability and kinetic inertness. So the reaction with cobalt complexes with oxygens are relatively sluggish compared to iron. And as a result, what happens, these systems are very useful, cobalt systems are useful to trap the intermediate, to understand the mechanism, but they are very slow in reactions. Sometimes the chemistry takes place, but they are very, very slow. And therefore, after some time, your system, your ligand backbone gets oxidized, because if you keep this system to oxygen or an oxidizing environment for a long time, your ligand backbones get cleaved. In case of manganese, we tried, but the synthetic compounds, so far we did not get any chemistry similar to that observed with iron systems.
Okay. Thank you, sir. You mentioned in one of your earlier slides something called an organic cofactor. So would you just elaborate a couple of lines on it?
Oh, sure. So let me take you into that part. All right. Okay. So can you see this slide?
Yes, sir, we can see it.
All right. So now here you see, as I said, that oxygen needs to be reductively activated. So oxygen needs electrons for its reduction. This sometimes what happens, that metal center provides electron and you can form an iron 3 superoxide. Then now you have an iron 3 superoxide species. But further reduction of iron 3 superoxide to peroxide or to high valent iron oxo, that requires further electron. In many enzymes, there is a very systematic, well synchronized electron transfer mechanism, where electron transfer protein like in heme system, cytochrome C oxidase, or in case of risky deoxygenases, I have shown you NADH provide electron through a risky cluster. But in this case, an organic compound like this keto acid, like ketoglutarate, they provide electron. And in this case, this keto acid itself undergoes oxidation. So the two electrons that are liberated in this oxidation process are utilized for the reduction of oxygen. So this is one organic cofactor which binds to the metal center. There are many other cofactors which may not necessarily be substrate, like ascorbate, like tetrahydroterine, like flavine, many different organic. So these are basically called electron bank. When you need electron, you can take up electron from there, and when you actually don't need electron, you basically give back electron to it, so it stores electrons. So they do reversible electron transfer. But in this particular case, alpha keto acid I showed, this is not something a reversible process. This is an irreversible process, and that's why I called, or we call this kind of organic cofactors as sacrificial reductants. So that means they sacrifice in the process but provides electron for a cause, and that cause is doing this oxidative transformation reactions. So many different organic cofactors are present in different enzymes depending on the reaction, depending on the enzymatic function, depending on evolutionary selection for a purpose, many parameters, depending on those parameters, these organic cofactors play a role. So flavine, tetrahydroterine, NADH, these are all organic cofactors.
Okay. Thank you, sir, for that clarification. And just one last question from my end. So you started with that very basic reaction of the oxidation of glucose by oxygen. So, sir, what is the source of electron there for the reductive activation of oxygen?
Okay, so you know this Krebs cycle, and you know this different the aerobic metabolism involves many different oxidative cycles, and there are many different enzymes are involved. And you know the product of the reaction catalyzed by one enzyme is in fact the substrate for another catalytic reaction catalyzed by another enzyme, and they work in a very synchronized way. And the electrons come from this electron transfer protein, depending on that reaction, or they can come from organic cofactors. And at the end of the cleavage from glucose, eventually get converted to pyruvate, from pyruvate to carboxylate, and then acetyl coenzyme A is involved, and at the end you get carbon dioxide. So in the process, a lot of energy is produced in form of ATP, which is stored in mitochondria. So many different reactions. I mean, not a single reaction. It's not a single state reaction. It's so many reactions. Krebs cycle, TCA cycle, Krebs cycles are involved. So these they use oxygen as the terminal electron acceptor, but the electrons are provided by electron transfer proteins or organic cofactors.
Thank you, sir. Thank you, sir, for this very informative lecture. Thank you very much for joining us, for giving us your valuable time.
Thank
you. We hope to be able to see you in the future webinars or hopefully seminars in the future.
Sure. We look forward to, we expect that it should be physical, right? Because this way,
a seminar is always more welcome than a webinar.
Right.
So we'll just have to wait and see.
Thank you very much, and thank you for having me here.
Thank you, sir. Thank you very much for joining us. Thank you. Okay, so we have come to the end of this session. We have come to the end of day one of our webinar series. Just a couple of announcements. So some of the registered participants have been inquiring about the Google feedback forms. So please just be informed, they will be available to you only after the completion of the entire webinar on September 24th. Once the last session of the last day is over, you will have the feedback forms emailed to you. And another thing is for the day 2 and day 3 of this webinar series, we'll be using a Zoom platform. So the link for that platform will be emailed to you prior to these webinar dates, and they will be emailed to your registered email IDs. I mean the IDs under which you have registered. So I hope you have all enjoyed this day, enjoyed the 2 sessions that we have had, and we hope to see you again for day 2 of our webinar series, that is on September 21st, Monday. Thank you once again for turning up in large numbers, and hope you enjoyed the day. Good night. Have a nice day. Thank you.